Hi everyone, welcome to Vedantu NEET English. I'm Diksha Ma'am, your chemistry master teacher. So how are you everyone? Everybody in the chat box, be active. Yes, bachcho. How are you all? Are you excited for today's lecture? I can't see the Josh in the chat box. Beta, firstly tell me, am I visible? Am I audible to all of you? Am I visible? Am I audible? Hanji. Am I visible? Am I audible to all of you? If yes, please write it down in the chat box. Fine, perfect, very nice. Very nice. Yes, ma'am. Yes, ma'am. So, where are my green hearts? Where are my green hearts? Fire, fire, fire. Green heart also I want. Let's spam the chat box with green hearts, okay? Let's spam the chat box with green hearts because your ma'am loves green color. Okay, so guys, in the last lecture, we did actually the basic of periodic table. Firstly, we talked about what was the history of periodic table, how modern periodic table was discovered. We discussed about screening effect. We discussed about how to calculate screening constant for different atoms, right? That we have discussed. So, any problem in last session? Any problem in the last class? Any problem? If you have any problem, then please write it down in the chat box. Yes. Okay. So beta, in today's class, we are going to focus on 2-3 things here. Firstly, we are going to focus on ionization energy, right? That means all the trends of periodic table. And you know what? The questions are asked from trends only. And that too, as you know, inorganic is very famous for exceptions. So they are going to ask you the maybe assertion reasoning questions based on the exception, that they will give you this is the trend, okay? This is the exceptional trend and what is the reason behind that. So you have to know the trend as well as the reason behind that, okay? So basically, I told you that it is divided into 4 blocks, S, P, D, F, right? P block is in detail in your syllabus, right? But still we will do like little bit of P block here also, right? We will do at least little bit of trends in P blocks, right? Then beta, we have DNF block that is also in detail in your syllabus, but we will understand little bit about that. Then beta, we have next thing that is S block trends and a period wise trend, right? So in today's class, we are going to talk about general trends and some of the exceptions that are generally observed in a periodic table, right? That is the first task. Now, what are these trends? Okay, there are few trends here. So what are these trends, everybody? What are these different properties? First is we will talk about atomic radius, right? You can say atomic size we are going to talk about. Then bacha, we are going to talk about ionization energy. Ionization energy, or you can say enthalpy, right? Third is we are going to talk about electron affinity, or you can say electron gain enthalpy, right? Electron affinity I am writing here. Electron affinity, there is a little bit difference between electron affinity and electron gain enthalpy, so we will talk about that. Then beta, we will calculate the electronegativities, the scales of electronegativities, right? Then now is a very important part that usually students skip. Now this part is the oxides. Oxides. Basically these are the applications of electronegativities, and after that you have oxides, hydrides, right? Acidity, basicity. Acidity and basicity of all these things. Oxides, hydrides, hydroxides. We will talk about the trends of basic, like increasing, decreasing order of basic or this character. So one thing I can tell you 100%, that is all the things that I'm going to cover today, you will definitely see questions from there. You will definitely see questions, right? The questions that are asked from periodic table are from this lecture only. The previous lecture, there might be one question from that, and the high chances about asking the questions is from this particular session, because in this session we are going to talk about the exceptional trends and the reason behind that. So that is very, very important when we talk about the NEET exam. You can even go through the previous year questions. NEET exam trends are asked frequently. Yes, beta. So let us start the session. Wait. I should put my phone on silent so that nobody can disturb us. Now, let us start the session, and firstly, we are going to talk about atomic radius here, right? First thing is, beta, we are going to talk about atomic radius here. So, atomic radius, right? That means, for example, you have this circle, right? What about this radius? Radius means the center to this point, right? That is when I talk about a circle, that is a 2D. Now, if I talk about a sphere, okay, if I talk about a sphere, this is how I draw a sphere in 2D, right? So, in sphere also, I will see the exact center point of this sphere, that from that point to the boundary of this sphere is my radius, right? Okay. Now, ma'am, but these electrons, they don't have a concrete wall, right? They don't have a concrete wall. Actually, they have a probability density, right? That they will be, for example, I talk about spherical, right? Spherical shape of S block, S orbital. Then it will be something like this, okay? It will be something like this, right? Here it will be too much, so many electrons, and there will be less electrons. So we are going to measure the distance from that nucleus to that point where the probability of finding the electron, right, is decreasing to that point that almost it is negligible, right? That point from where we can say that after this point the probability is very less that we can completely ignore that electron. Even if it goes out of that, we can completely ignore that. The high chances are in this sphere, right? So we will try to calculate, okay? So that is basically called that, what we call that, we say that this is the positive and this is the atom, right? This is the atom. Now this is the atom. Now this is the distance from this nucleus to this thing, that is called the radius. Now beta, I don't, it's not like atom is like this big, right? Atom is not even this, right? Atom is beta not even, just a minute, atom is not even this, right? Atom is not this, atom is not even this much large, atom is not even this much large. Even in this particular ball, there will be millions and trillions of atoms, right? So that means I cannot measure the atom like that, okay, this is my scale and I will measure the length, right? That's not possible. So how do we measure it? How do we measure it? For that, beta, what we will do, firstly we need to understand that there are 3 type of radiuses, right? And we will calculate that with the help of a distance, right? First, beta, that is, first we have, for non-metals we have covalent radius, right? Then we have metallic radius for metals, metallic radius. There are 3 types, na? Then we have van der Waals radius, right? Van der Waals radius. These are the 3 kind of radiuses that we are going to talk about, right? So this is applicable for non-metals, this is for non-metals, this is for metals, this is for metals, and this is when I am talking about 2 molecules here, right? When I am talking about 2 molecules, I have so many molecules here. Wait. For example, if I talk about van der Waals radius is something, for example, there are 2 atoms, okay, through atoms. They are not bonded to each other, right? They are not bonded to each other. Like they are not sharing anything. There is no kind of bond here, right? They are 2 individual molecules or atoms, right, that are placed at a certain distance. Then we calculate the van der Waals radius. Now, in depth, we are going to talk about all these 3 things. First is covalent radius, right? Covalent radius is when there is bond between two atoms, like they are sharing some electrons here, right? They are sharing, there is a proper bond. Whenever we are talking about bond, there is something like this, right? There is a bond between these two things. When there is no bond, it will be like this, right? Or it will be like this, right? So that will be when there is no bond here. But in this case, they are sharing the electron. That means they are completely bonded to each other, right? So in this case, how do you find the radius, right? So how you will find the radius? For example, this is one atom. You can see this is the boundary. This is the second atom. This is the boundary, right? Now this is the center of atom A. Let us talk about this is A. This is B. This is the center of atom B. So we will calculate the distance between two atoms with lot of spectroscopy. We will calculate that, right? This will be calculated based on the spectroscopies, right? Then beta, we will calculate the distance between these two things. We will calculate the distance between these two things. Let us consider that as DAB. Okay, I am thinking that this particular compound is a homonuclear compound. Okay, I am thinking that this particular compound is a homonuclear compound. Okay, so basically there are two kind of compounds, right? Okay, I'll teach you also 2-3 formulas here. Okay, see, homonuclear means, that means AA. If this is hydrogen, this is also hydrogen, right? If this is of hydrogen, this is also hydrogen. This I am resembling the point. Okay, this A is the point, this B is the point. Okay, so don't get confused here. Or I will just say this, for example, this is HH, or anything you can say. It is BB, you can say XX, we can take, right? Because I don't want you to get confused between this AB and this X. This is the name of the atom, that is same. These are two same atoms, right? So for two same atoms, the full distance, that is distance of AB, will be equal. So for a more easy thing, what you can do, what you can take this particular thing as, this is also a distance, right? This is also the center, right? Then take the atom as AA only, right? The molecule is A and this is also A. The distance between these two is DAA, that is equals to 2 into RA, right? I have two molecules, I have two same balls, right? I have two same balls, same atoms. These are two black same atoms. When they make a bond with each other, right? When they make a bond with each other, what I will say, I will calculate the distance from the centers. Then I will divide it by 2. Then I will get the radius of one atom only if the atoms are same. Here the atoms are same. Now we will talk about if the atoms are different, right? Now let us talk about hetero. If the atoms are different, right? Hetero, if atoms are different. For example, AB, right? And there also you have two things. Either though, they both will have electronegativity. See, if both the atoms are same, hydrogen, hydrogen, oxygen, oxygen, nitrogen, nitrogen, electronegativities are same only. But if they are different, that means there will be electronegativity difference, right? Okay, there will be electronegativity difference. We will talk about electronegativity in detail, right, in today's lecture only. But if I say delta X is the electronegativity, now this is very small, right? Very small. Or you can say electronegativity of A is approximately same to electronegativity of B, right? But here electronegativity of A is not equals to electronegativity of B. So there can be two conditions to that, right? Either electronegativity will be same or electronegativity will be different. If I talk about, there are two different atoms here, right? Okay. So if electronegativity is almost same, right? It's not like one is very powerful and the other is very less powerful, like HF. If I talk about HF, like the molecule, I can say HF. Now in HF, you can say this H and F, right? F is most electronegative atom, right? So there is a large electronegativity difference between these two molecules, right? But there are some molecules where the electronegativity difference will be very low, right? Very less, right? Or you can say nitrogen and oxygen, right? They have very less electronegativity difference. So we can talk about those kind of molecules, those kind of atoms when they bind together, right? So in this case, beta, there is simple thing that we will say d distance of A and B will be equals to radius of A plus radius of B. That means I have two different molecules here, right? I have two different molecules here. Okay, one is this brown one is this one, right? You can see one is large, other is small, right? If they have same electronegativities, then what I will say that the distance of this particular and the distance of this particular, the radius of these two combined together will form the distance, right? That means if I say this is your one molecule, this is the other, this is the other one, right? This is the other one because they are different. This is the center, right? And this is the distance. This is the full distance. And this distance is called DAB. That will be equals to radius of A plus radius of B. Because they have almost same electronegativity. There is no pulling of electron. There is no very large pulling of electron, right? If there is pulling of electron in a very large extent, then the structure is going to change a little bit, right? That means if the electronegativity is not equal, right? There is a large electronegativity difference between them, then things are going to change here. You cannot just directly apply this formula, right? That is not possible because this distance, right, this gap is going to be so large, right, that you cannot say that DAB will be equals to RA and RB, right? Here it will be very small, but in that case it will be very large. So there will be some kind of like different things that you cannot apply this particular formula directly. So there are two formulas that you need to apply here, right? Okay. So there are two formulas. I will write it in the next page only. Two formulas that you will apply here. First is, okay, let me write it in the next page only. I'm writing it here that you will have this kind of thing, right? So this is A and this is B. So let us see now what will happen. Let us see now what will happen, right? So in this case, you will have two things, right? You will have two formulas. What are these two formulas, right? Frankly, the questions from these two formulas are hardly asked in NEET, but still I will teach you that, okay? Porterfield, first formula is Porterfield formula, right? Porterfield formula, right? Then the formula, name of the formula is Sterenson and Shoemaker, right? Sterenson and Shoemaker. You can learn it by Shoemaker. Now you just need to learn the formula, that's it. Okay, there is no other thing here. This is the thing, the formula is very easy. Here the formula is very easy, right? Here RA will be equals to DAA by 2. Very simple. It is also very simple. Here the formula will change, right? In this case, you have two formulas. First formula will be radius will be, or you can say distance will be, distance of AB is going to be radius of A plus radius of B. Here you need to know the electron negativity, right? You need to know the electron negativity. Delta X is the electron negativity, right? Or I will write here only delta X is the electronegativity, right? That is the electronegativity. Now, this is the same kind of formula, but this will differentiate here, right? The same formula, but this will differentiate. The answer will be in Armstrong, okay? This is DAB, RA plus RB, same formula it is, minus 0.07. This will be delta X square. So there are two formulas. First is Sterenson formula and Shoemaker, then is Porterfield formula. Now, application of formula is very simple. For example, they have given you this is the radius of one atom, radius of second atom, the electronegative difference of A atom is this. or they can tell you the electronegativity of A atom is this, B atom is this. Then you subtract the electronegativity, you will get delta X, and put the values, you will get the answer. Very simple. But remember, this will be in angstrom. Okay, that will be in angstrom. Okay, till here any problem? Till here any problem? Three things we did that. Three kind of things we have. Covalent radius, firstly, this is for non-metals that we have already calculated. Non-metals can have different electronegativities, same kind of electronegativities, or atoms can be same here, right? 2-3 things can happen here. Now, let us talk about the metallic radius. So, metallic radius, if you remember the model of how metals are arranged, how atoms are arranged. This actually is atoms are arranged like this, right? It's not like they are sharing some electron or anything like that. The electrons are like these are the kernels. The electrons are placed in between, right? And they are vibrating, right? They are vibrating. It's like this kind of model, right? So that means the atoms in a metal like will be very close to each other, like they will be like totally together, like this. They will be completely binded to each other, right? For example, I have a box in a very tight manner. I put all the atoms there, right? I don't have any box here. If I put all the atoms there, what will happen? These are actually these will start to vibrate, right? These will start to vibrate. That is the model of a metal, right? How atoms are arranged in it. So this we can say that atoms looks like this in a metal, right? So how to calculate the distance between them? For example, this is the center. This is also the center. Now this is called the D A, you can say same or different, will be same only, right? So that will be equals to radius of A and radius of this, right? So you can say that DAA equals to 2 into radius of A, and answer will be radius of A is equals to DAA by 2. Okay, ji? Understood? Because when we talk about this thing, we are talking about the same atom only, right? Okay. Now, next thing is van der Waal. Van der Waal means, for example, you have one molecule here, you have one molecule here, right? And the distance between these will not be totally like binded to each other. It will not be like this. In the metallic radius, it was like this. They were very like, there was hardly any distance between them, right? Hardly any difference between them. But in van der Waal radius, there are two different molecules or atoms. They are not stick to each other. They are little bit away from each other, right? So what we will calculate, this is called the van der Waal attractions or van der Waal radius we are going to calculate. That is this thing, right? This is the distance they will have. We are going to calculate the radius here. So how you will calculate that? How you will calculate the radius, van der Waal radius? This is a simple thing, right? Very simple thing. This also doesn't require any formula or anything here, right? Any formula is not required here, right? So approximately you will say DAA will be equals to 2 times of RA, right? This you will say, ma'am, here also you are saying this. Here also you are saying this. Here it will be exactly. The distance will be so less that it is almost negligible, right? The way of calculating it is same, right? You will say it will be slightly more. If this is the radius now, you will calculate the radius as this thing, right? It will be slightly more than the actual radius when you calculate the van der Waal radius. When you calculate the radius of any atom, when they are not connected to each other, they are in a van der Waal forces, then you will not be able to calculate the exact radius, but little bit more than that, The formula is same, but the correction will not be same. You will find out that if you have, this is the same radius, this is the same atom, this is also the same atom. Now you have sodium atoms, right? They are actually in a metallic bond. Here you will find the radius as exactly, mostly you will see little bit difference only, right? But here what you will calculate, the radius will be slightly more than what you expected, Why? Because they are in the van der Waals forces. They are not in the metallic forces. They are not covalently bonded to each other, right? In the covalent radius, beta, in the covalent radius, because they are bonded to each other, they are sharing the electrons. You will see that in comparison to the exact radius, that is in reality, it will be slightly less than that, right? But when we talk about metallic, it will be somewhat similar to the actual radius, right? But this is going to be slightly more than the actual radius, right? Otherwise, we will call all of these radius only, right? Okay, the formula is going to be same only. Yes, but beta, when I talk about that, you have calculated radius of some atom, right? You have calculated the metallic radius, you have calculated the van der Waals radius, you will calculated the covalent radius. Now, can you tell me which radius will be maximum? I am talking about H2, right? I am talking about H, hydrogen radius, right? Or you can say hydrogen that doesn't exist in a metallic form. Let us talk about sodium. First, you calculated the radius of sodium with the help of covalent bond. Then you calculated it with the help of metallic bond. Then you calculated it with the help of van der Waals forces, right? With different atoms. Now, what you will observe that in that case, the covalent radius will be less, then there will be then there will be metallic radius, and maximum will be van der Waals radius, right? This is what you are going to see, and this is a very important conclusion from this, right? This is a very important conclusion from this, that RC, then you have Rn, then you have Rv. Okay, Ji? Understood? Maximum is of van der Waals. Then there is metallic. Then there is covalent. Why? Reason. Reason is, someone asked you, the reason is very simple, that here it will be like this. Okay. Here it will be like this. Here it will be like this. Two atoms who are at a nearest neighboring distance. Right? Nearest neighboring distance means as close as it is possible. Right? They are not stick to each other, but the closest distance that we can imagine in a van der Waals force. In metallic, it will be stick to each other, right? They will be stick to each other, right? There is no actual distance between these two atoms, right? Then we will talk about covalent. It will be like this. Yes, it will be like this because they are sharing the electrons here. It will be like this. That is why van der Waals radius is maximum. Then you have metallic. Then you have covalent. Yes, beta, any problem here? Any problem here? Simple logic. Simple logic. Yes, bacho. Okay. Yes, very good. Then, bacha, we have second thing, that is variation of atomic radii in a period. Right? Now, we are going to talk about trends here. Right? We talked about simple things. When I talk about atomic radii, na, it is the approximation of all of these things. It is the approximation of all of these things. Right? Okay, that was calculated experimentally also. Then, beta, we have variation of atomic radius in a period. Firstly, all the trends, beta, we are going to do along the period, down the group. Along the period, down the group. That means left to right, top to bottom. Right? These are the two things that I am going to talk about in today's lecture. Right? So now, before this, last time we talked about screening effect. Right? Screening effect. So you need to know the variation, 2-3 things here. When I will talk about period, when I will talk about a period that is left to right, that means along the period, then I will always say that Z effective is increasing or decreasing, everybody. See, you have two things here. First is period, second is group. Now, the base will always be Z effective, right? The base will always be Z effective. See, in a period we will talk about, for example, this is NS1, this is NS2, this is NS2, NP1, this is NS2, NP2, right? It will be like this. It will be like group 1, group 2, group 13, group 14, right? It's like this. That means there is addition of one electron. It's not like one new shell is added here. The principal quantum number is same here. No new shell is added here. There is just one electrons that are being added here. That means when I talk about the screening effect, see, when I talk about the screening effect, or when I talk about the Z effective, right? So Z effective is going to increase. Z effective is going to increase here. That means the nuclear charge is going to increase here. It is going to attract more electrons here, right? It is going to attract the electrons because the number of shells is not increasing here, right? The number of shells is not increasing. This is one electron that is being added there, right? One electron is added, one proton is added. One electron, see, understand this in this way, right? For example, you have earlier this atom in a period I'm talking about, right? In a period I'm talking about, earlier you have this thing, then you have this thing, right? Then you have this thing. Just simple imagination, right? Now there is one electron, there is two electron, three electron, four electron, right? Let's see the logic behind that. Here you have one proton, here you have two proton, here you have three proton, here you have four proton, right? Here you have four proton. Now what will happen in the screening effect? This proton is going to attract this electron, right? Ma'am, here you have two proton. The charge, the nuclear charge is going to increase, right? But you will say, ma'am, electron charge will also increase, right? Ma'am, screening effect will also increase. But beta, the number of shells are not increasing that much. Then electron is just one electron is added here, right? So down the group, when you will see the shells are increasing, right? Down the group, the comparison is like this. Down the group, the comparison is like this. It's like this atom, then you have this atom, then you have this atom, right? And slowly it is going to increase only, right? It is going to increase only. That means the shells are increasing here, right? If you have here n, it will be n plus 1, it will be n plus 2. This is the principal quantum number, right? So principal quantum number is going to increase here, right? So many electrons will be added here, so many shells. So down the group, what you will write that here number of shells increase, number of shells increase, right? And here what you will say, here beta, what you will say, because all the other things will be based on this particular stuff. Z, as you can see, the electrons are same, right? So screening effect, that means sigma is going to decrease here, right? Sigma will not be that much, right? Sigma will not be that much. These two protons, right? They will be attracting. The shielding will not be that much, right? Because only one electron is getting added and the same amount of proton is getting added, right? So proton is going to attract that electron and going to, because this proton is actually at a stable position. This electron is not at a stable position. This electron is moving here and there, right? When your watchman is not at a stable position, right? He's moving here and there. For example, this is how there are 10 houses. The watchman is moved to 10th house, but the thief came to the first house, right? So that means when something is moving, it will not be something that you can rely on, right? If your watchman is actually standing outside your home only then you can rely on that watchman. Otherwise, okay, in the blink of an eye, something can happen, right? In the same way, this electron is revolving here and there. That is why these two protons are able to attract the outermost electron here, right? So that means Z effective, right? Nuclear charge, that proton is going to act on the outermost electron, that is going to increase. It is going to attract that electron inside, right? It is going to decrease the size, right? So what you will write here, Z effective will increase here. If Z effective is increasing, attractions are increasing, right? Just three things that you need to understand, that whenever along a period screening effect decreases, Z effective increases, attraction, you can understand this with the help of a watchman example, right? That is why screening effect, that means he is not able to take care of everything, right? So attraction increases, the attraction of the thief will increase, right? The thief is at a stable position, he has this target. I will today I will my target is house number 2, but the watchman has like, I have to take care of all the houses in this society, right? That is the reason. So attraction is going to increase here, right? But in the shell, what you have, the number of shells is increasing. As the number of shells is increasing, what will happen? Firstly, those shells are being added here. As shells are being added here, so that is why the Z effect is not going to dominate over here. That is why the size that you can see, repulsions are going to increase. Repulsions are going to increase here. Z effect is going to decrease here. Okay? Repulsions are going to increase here. Okay, beta? Okay, beta? Or you can also write it here that sigma will increase and Z effective will decrease. Right? One of the student is asking, ma'am, what is sigma? Sigma beta, that is screening effect. I told you yesterday, na, we calculated the sigma value for different atoms. We calculated that, right? We calculated sigma value for different atoms. That is sigma only. Okay, that is the shielding effect, screening effect. The shielding of the electron. I told you na yesterday that you have this atom, right? When there is penetration effect, because of that the electron will come closer to the nucleus. There will be penetration. They will be inside the, almost very close to the nucleus. That is the reason they will make a very hard density of electrons over that nucleus, and that is why they are going to shield. That means that they are going to bodyguard, right, which nucleus from the outermost electron. So the effect that nucleus is going to draw on the outermost electron, that will not be drawn. That is why there will not be full nuclear charge that this nucleus can give to the outermost electron. Only there will be Z affected. That means nuclear charge minus the shielding effect. Yes? Okay? Yes, beta? Chal. Now, next thing here. Now, if you understood this concept, then let us start the variation of atomic this in a period. So when I talk about along a period, what will happen? You just need to understand this one thing, that along a period, beta, who all are asking me na that, ma'am, what is this? Ma'am, what is Z effective? What is screening effect? Beta, please watch the last lecture, because I think I have completed that screening effect in 1 hour in detail, in detail. Right? So please go through that, only then you will be able to understand this. Right? Okay. But now for today's class, I have told you this thing, right? That this is Z effective, nuclear charge, nucleus, right? Electrons will penetrate because of the because of electrostatic forces. Nucleus is going to give to the electrons, and then you will feel that inside, if this is the nucleus, you will feel there is electron density, heavy electron density, right, on that nucleus, which is going to screen this nucleus from giving the nuclear charge to the outermost electron. And that is how Z effective, that means a nuclear charge that originally this nucleus is going to give to the electron minus the screening, this bodyguard, right? Okay. Now, let us understand this thing, that along the period, what happens? So along the period, first you always remember Z effective. We are going to do everything with this help. Z effective increases, attraction increases, right? Attraction increases. If Z effective is increasing, it is pulling the electron. This nucleus is pulling the electron, right? So what will happen? The size is going to decrease here. So you will write the size will decrease. The size will decrease here. Then beta, what about group? What about this group? What about this group? In a Z effective, right, in down the group, what you will see, the number of shells are increasing, right? And that is why screening effect is increasing. The shells, lots of electrons. The valence are increasing. I told you one thing. Nucleus is the heroine, right? And the outermost electron is the hero, right? And all these other electrons are the valence, right? So that is why the valence are increasing. When the valence is increasing, then what will happen? It will be very difficult for the nucleus to attract the outermost electron, right? Heroine and hero will not meet in this movie. So what will happen? this will happen that this is not going to attract it. That is why there will be increase in the size. So down the group size will decrease, right? You will say number of shells that is going to increase. That is why size is going to increase here, right? That is why size is going to increase here, right? Okay. Yes, beta. So one by one, let us do the exceptions. Let us do the exceptions. Okay, this you can see that from here size is decreasing, 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 and down the group size is increasing, increasing, increasing. Now let us do the exceptions from where actually this, this comes. Paper comes, right? The first part, there is no power here. I don't know why only in your class, whether I take it in the evening, whether I take it in the morning, this never happens, right? But whenever I'm taking your class, this will definitely happen. This is going to happen definitely. This always happens when I take your class. Why God, why are you doing this to us? You don't, like, this light is what? These are the electrons that are shielding, right? That are shielding us, right? I am the nucleus, you are the outermost electron, and this light is, making it very difficult for me to teach you. I'm waiting for the light to come. Yes. Now, beta, let us talk about this particular thing, that how along the period, this is along the period, right? This is down the group, right? This is down the group. Now, let us see what is going to happen. So, you can see this is along the period lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, right? The size is decreasing, 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 right? And here, beta, this is increasing, 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 right? This is the graph that is in your syllabus, right? You can see the size is increasing, here the size is increasing. I have told you the reason behind that. But there is one exception. What is that exception? That exception is, wherever I will write exception, that is important. That exception is noble gases, right? That exception is noble gases. Noble gases. Now, beta, what about these noble gases? Now, these noble gases, they have the largest size among them. Why so? What is the reason behind that? What is the reason behind that? Everybody. Everybody. What is the reason behind that? Can you tell me why they have there is separate channel? Yes, there is separate channel for Hindi, beta, right? This is the English channel, written as Vedantu NEET English. Now, if I talk about noble gases, they have the largest value among them. For example, if I talk about this lithium wala thing, right? So it will be lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Then there will be neon now. So neon will be at the first position. It will be like this. This will be the largest. So the group 18th will be at the first position. It will have largest value. Can you tell me what can be the reason behind that? Can you tell me what can be the reason behind that? Any idea on that? Any idea on that? I am trying to see the answer here, but you guys are not giving it. So yeah, as you can see, noble gases, that means Sant Mahatma, right? They don't interact with each other, right? They actually are like van der Waals forces only. They are connected to each other with the van der Waals forces, different atoms, like they are connected, they are attracting to each other with the help of van der Waals forces. That means here we are going to calculate the van der Waals radius. That means we calculate RV. That is van der Waals radius. Van der Waals radius. And as I told you, van der Waals radius is the maximum. Firstly, van der Waals radius, because of the distance, right? That is why they have the maximum radius out of any other radius, be it covalent, be it metallic. That is why they have the maximum radius among the period, right? Among the period, firstly there will be group 18, then 1, 2, 3, 4 and so on, right? Okay, bachcho? Yes, beta. Then we have second thing, that is D block, right? We talked about this thing, right? We talked about this thing here. We talked about this thing, that how in this particular second and third period it is going to move, right? This is going to decrease, this is going to decrease, but this neon and argon will have maximum, right? Now let us talk about this 3D, right? Now let us talk about this 3D series, right? So in this 3D series, what you are going to see, this is the graph that you will see. We will do that in detail in DNF block. But now you need to see this thing, that there is no regular trend that you will see here, right? You will see that firstly it will decrease, then it will be approximately same, then it will increase here, right? Firstly there will be decrease, then nearly same, then it will increase here. That means here it is going to decrease, then it will be nearly same, then increase. Now what is the reason behind that? Now what can be the reason? What can be the reason? As you know, in these kind of in 3D series, there are d electrons also involved here, right? So firstly beta, what will happen here? Z effective is going to dominate, right? Here Z effective is going to dominate, right? And here Z effective, and here Z effective and shielding effect are going to be like in a big competition. Like there is shielding effect, there is Z effective. They are like in a boxing marathon or something, right? So what will happen here? Firstly, Z effective will dominate. It will give a punch to the screening effect, right? So it will win till chromium, and that is why size will shrink. It will decrease, and here they both will be equal, right? There are some points now in cricket also. What you see, sometimes one is dominating, sometimes the other team is dominating, right? Sometimes they are both are playing equally, right? So here they are playing equally, and in the last two, in this case, what will happen? Shielding effect will dominate, right? Shielding effect will dominate, and that's why here size is going to increase, right? And that is why size increases here. Okay beta, that is why size increases here. Okay beta, yes. Now let us talk about down the group. There is one exception. Now what is that exception? Down the group, what should happen? Down the group the size should increase only, right? But here you have something, here you have inner transition elements, right? Here you have 4F series. Now because of this 4F series, what is going to happen, right? What is going to happen? The size of, the radius of, very important, the radius of 4D and 5D series is approximately going to be same, right? It will be approximately same, right? So what will happen here? Because of the 4F electrons, you know now here what happens? Here you have only 3Ds involved, right? Here only 3Ds involved. There is no 4F here. There is no F orbital. There is no F orbital here. But after lanthanum, you have 4F, right? From here, you have 4F orbitals, right? In hafnium and all the other elements in this series, 4D, 5D series, what will happen? There will be 4F orbitals, right? And you know what is the screening effect? Screening effect is like this: S, then P, then D, then you have F. It has the lowest screening effect, right? It has the lowest screening effect. So what will happen? Usually what should happen? The size should increase down the group, right? So it should increase down the group. So what should happen? If this is 4D series, this should be the 5D series, right? This is 4D, this should be the 5D series. Down the group, size should increase. But what exactly happened? Exactly what happened? This was the 4D series, this was also the size of 5D series. Why so? Because the 4F orbitals, right, they have very poor shielding effect. In this case, in this particular case, what happened? These 4F orbitals were not able to protect the outermost electron from the nuclear charge that the nucleus is giving, right? That is why the electron got attracted, and the size of this 4D series and 5D series became almost similar, right? In 5D series you have 4f and this becomes almost similar. That is the reason there are so many questions based on this, that zirconium, hafnium have same size. So the size of these elements will be same, right? That is called the lengthenoid contraction, right? The name is lengthenoid contraction. There is a proper name given to it, that is lengthenoid contraction. Why this is so? Because of poor shielding effect of, poor shielding effect of 4f orbitals, right? Because of poor shielding effect of 4f orbitals, this happens, right, beta? Okay. Now let us talk about the other thing. Now beta, this is about f orbital, right? Again, I've just told you that you will see europium, you will see an exception, usually it is decreasing, and ytterbium you will see an exception here, right? So basically in f orbital the trend is not very consistent or something like that. It is very abnormal trends that you will observe in f orbitals, right? Again, we are going to do this in detail in DNF block, right? Okay. Now let us talk about the exception here. A very important question. All these questions, okay, this has also been asked so many times, this has been asked so many times, right? Then this question has been asked so many times, very, very important. Now this question also was asked so many times in your PYQs, you can see, right? Down the group, what you expect, that what should happen? बाल गए Indian tail se, Indian tail, right? So what should happen exactly here? What should happen? The size should increase. The size should increase here, right? Okay, the size should increase. But something weird happens here, right? Something weird happens. What is that weird thing that happens here? See, if in periodic tables you see this carefully, this is boron aluminium. From gallium, you will see 3D series is going to start, right? From gallium, you will see 3D series is going to start. Because of the 3D series, now you know that this depends on the shielding effect, right? And these d electrons have a very poor shielding effect. sp, and then you have d, then you have f. Earlier, this aluminium had no d electrons. It only had s electrons, but this also has d electrons. So these d electrons are not have very good shielding effect. So what will happen? They will not be able to protect the outermost electron. So the size is going to decrease here, right? The size will decrease so that the size of aluminium will be more than this, right? The size will decrease so that the actual order you will see, it will be B, then you will have gallium, then you will have aluminium, then indium, then thallium. And also one more thing, the size of indium and thallium is also going to be approximately equal only, right? And this is going to be the actual trend. This is going to be the actual trend that you will observe here, the real actual trend, right? Now, can you tell me the reason behind this? Here you had the involvement of 3D series, because of that size decreases, poor shielding effect, right? You can write here poor shielding effect, poor shielding effect, poor shielding effect of 3D electrons, right? Poor shielding effect of 3D electrons. But here what you can write, here what happened? Can you tell me what here happened? You can go through the periodic table again, right? Now, what exactly happened here? This is indium, right? This is indium and this is thallium. Now, as I told you, the size of these two is going to be approximately same. Why? Because in thallium what happened? After this lanthanum, you will have 4f orbitals, right? And because of the poor shielding effect of these 4f orbitals, the size again is going to decrease here, right? There is no name for poor shielding effect of 3D electrons, but there is a name for poor shielding effect of 4f, that is called lengthenoid contraction, right? So lanthanoid contraction is going to happen. The size will decrease. That is why here nothing is happening. In indium, nothing is happening. In thallium, the size is going to decrease and approximately similar to that. But in some books, you will see that in some books, beta, in some books, it is also written like this. In some books, it is written indium is less than this. In some books, it is written approximately same, right? So both are true, right? Right? Both are true. Okay, but yeah, this is more correct. That approximately equal is more correct. Okay? Yes, beta. Yes, bacha. Lanthanoid contraction. Okay, any problem here? Let me see, beta, if the light is going to come or not, or otherwise I will take the class tomorrow. Okay, everybody, because in the evening you have Gopika ma'am's class. So let me see, because there's the backup will also go, na? The backup will also, there's a heavy setup that is there. So what happens for 1 or 1.5 hours, so it can resist, but after that it will not be able to resist, right? So I will see in 5 minutes. I will call the electricity board if it is going to come or not, because the weather is not right here. There is so many thunderstorm and all is happening here. So there might be issue with that. So if they are saying that okay, the light will not come, there is power cut for a long time, so what we'll do, we will take the session tomorrow, right? Okay, I will complete the chapter tomorrow. Okay, bachcho? Yes. Now, next is, let us do the questions here. 2018 question, beta. 2018 question. The correct order of atomic radii in group 13 elements, right? A, B, C, D, everybody. A, B, C, D. A, B, C, D. A, B, C, D. What is the correct order? Let me see through the app when the power cut is. Okay. Answered it. Very good. Now, as I told you, there you will see the change here, right? Boron, gallium, indium, boron, gallium, aluminium, indium, thallium, right? So, answer is going to be D is the correct answer, right? D is the correct answer, right, bachcho? Then the next question, this was asked in NEET 2018, right? NEET, that is the latest, right? You can see a very simple question. They can even ask you the assertion reasoning question, that why this happened. The reason will be written as because of lanthanoid contraction, because of high shielding effect of 3D, because of poor shielding effect. So what will the answer? That will be poor shielding effect of that, right? Now, next is, in which pair the second atom, is larger than the first. Now, this boron chlorine, this is actually fluorine, chlorine, bromine. That means down the group size increases. That means chlorine should be bigger than bromine, right? The first atom should be larger, but here they are saying bromine should be larger than this. So that is incorrect. Here sodium should be larger than magnesium, right? So sodium is like this, sodium, magnesium, right? They are along the period, size decreases. So this will be lithium, beryllium, boron, carbon, nitrogen, oxygen, sodium. Along the period, second element is larger. Wait. Second element is larger. That means they are saying chlorine should be greater than bromine, magnesium should be greater than sodium, strontium should be greater than this, or phosphorus should be greater than this, right? Second element is larger. Calcium should be greater than strontium. Oof. chlorine is greater than bromine, then you have magnesium is greater than sodium, then you have calcium is greater than strontium, then you have phosphorus is greater than this. When you talk about down the group, size is increasing. So bromine is greater than this, right? Bromine is greater than chlorine. That is incorrect, right? Magnesium or sodium, if I talk about sodium and then there come magnesium, right? It is along the period, size is decreasing. So this will be greater than this. Again, this is incorrect, right? Calcium, strontium, right? Calcium, strontium, that is in the same group, right? Down the group, right? So down the group, beta mange car, scooter. So that is down the group. Down the group, it should be, strontium should be more than that. This is also incorrect. Now, this is 15th group. Nitrogen, then you have phosphorus. Down the group, size increases, phosphorus will be greater than this, which is true. So D is the correct answer. Right? D is the correct answer. Right? D is the correct answer. Right, beta? Now, let us talk about ionic radii. Beta, let us talk about ionic radii. I think the light is not going to come. Okay. So, next is beta ionic radii. So, when I talk about ionic radii, firstly, let us talk about cations, anions, and simple neutral atoms. So, when we talk about these three things, so always remember that the size of cation is always less than you have neutral atom, then you have largest will be anion. That is the first thing that you need to remember. Okay, that is the first thing that you need to remember if you have same atom. Now, if different atom, now we are increasing the charge on cation, right? Or you can say cation charge, cation charge, cation charge, right? Is it increasing or decreasing? Right? Then you have anion charge. Then you have anion charge. We will talk about the size here. Now the cation charge means you are taking away the electron. Right? Earlier it was A positive. Earlier it was A. Now you have taken away one electron, that is A positive. You have taken away two electrons, that is A2 positive. Right? So proton is not you are taking out. You are not taking out the proton there. The proton is intact, right? What exactly is happening here? Right? You have this A. This is the positive, right? The positive is as it is. You have 2, 3 electrons, let us say 2 electrons, right? Then if you take away one electron from here, the electrons are decreasing, but the proton is not decreasing, right? The proton is same. The same nuclear charge is applied on less electrons then. That is why the size is going to decrease here, right? The size is going to decrease here. The cation charge increases, that means the size will decrease, right? But when you talk about you are adding the electrons, right? I am adding the electrons. I am adding the electrons here. So what will happen? So if I add the electrons, I am giving it electrons. So the same proton is will have to act on more protons now. Right? For example, you have 10 chocolates, right? You have 10 chocolates. Chocolates are constant, right? It's your birthday, you have 10 chocolates. So what happened? Firstly, though, you had 10 friends only. You thought, okay, 10 friends will come today, right, in the school. So what happened? Seven actually, 3 were absent, 7 were present. So what happened here? Because 7 were present, you have more chocolates. The chocolates are constant, right? The chocolates are constant, right? This is decreasing, right? That is why size is, now you can distribute more chocolates to one person, right? You can say, okay, you can have little more of chocolate you can have. But if somehow those friends who told you that I am going to be absent, right? You saw 13 friends. So now you have 10 chocolates, you have 13 friends. So you will have to give less chocolates to each person, to each friend, right? There will be less amount of chocolate that will be given to each friend. The same thing that happened, that when you're adding the electrons, same proton is going to act on so many electrons. That is why it will not be able to attract it. So size is going to increase here. Size is going to increase here. Right? Size is going to increase here. Right, beta? Okay, beta. Size is going to decrease here. Increase here. Any problem here? Any problem here? Now let us talk about isoelectronic species. Isoelectronic species. Isoelectronic species. What are these isoelectronic species? I told you in structure of atom, which have same number of electrons. These are the isoelectronic species. So in isoelectronic species, you need to remember that when we are talking about same number of electrons, they are isoelectronic to each other. The ionic radius is going to inversely proportional with the atomic number. For example, if I say that, let us talk about one example here, right? Let us talk about one example here. Let us talk about one example. Oxygen. Now you tell me these are isoelectronic to each other. Or one more I can write here, magnesium 2 positive. Now they are isoelectronic to each other. That means same electrons, 10 electrons in each of them. 8 plus 2, 10, 9 plus 1, 10, neon 10, sodium 11 minus 1, magnesium 12 minus 2. All have 10 electrons. Now I'm telling you that as atomic number is increasing, right? See, why this is so? Because proton is same, no? Proton here it will be 8 only. You are adding 2 electrons here. Proton is going to be same. The number of chocolates are same. The electrons are 10 here. Here the electrons are 10. Here proton is changing basically. The electrons are 10 only. Right? Here proton is 8. It has 8 proton. It has 9 proton. It has 10 proton. It has 11 proton. It has 12 proton. So that means more nuclear charge is acting on those 10 electrons. So here the size is going to decrease. Right? That is why I told you directly that as atomic number will increase, the ionic radius is going to decrease because the protons are more. Here you have 10 electrons, 10 electrons, 10 electrons, 10 electrons, 10 electrons. Right? Okay. It is like oxygen is your friend. He also had 10 friends, but he took 8 chocolates. Right? He also had 10 friends. Who took 9 chocolates. He had 10 friends. He took 10 chocolates. That means equal, right? He had 10 friends, he took 11 chocolates. 10 friends and 11 chocolates. He will have to, 10 friends and 11 chocolates, it will be good, right? That it can give more chocolates to one friend, right? That means the size is going to decrease. More chocolates means more nuclear charge it can give. More nuclear charge means it can attract the outermost electron there. Right? So directly you can you can learn this by this logic, or you can directly understand this thing that ionic radius is always inversely proportional to the atomic number. Okay? ठीक है जी? Okay बच्चों? Yes? Now, what is the answer to this one? What is the answer to this one? Which of the following order of radii is correct? Which of the following order of radii is correct? Which of the following order of radii is correct? Lithium, beryllium, magnesium. Okay. Lithium, beryllium, magnesium. That is going this way, right? So you can say lithium, beryllium, magnesium. It's like this, right? It's like this. Here it is decreasing. Here it is decreasing. So this becomes wrong here. Lithium is greater than beryllium. So this is wrong. Okay. This becomes wrong. So this option is not correct. Right? This option is not correct. Now you have 3 things here. That is oxygen, O2 negative, O2 negative, and you have N3 negative. Right? Oxygen, O2 negative and N3 negative. Right? Now, these are not isoelectronic species. But here you can see the charge is increasing. The anionic charge is increasing. The anionic charge increases, what will happen? Here you have 8 protons, 8 electrons. Here you have 8 protons but 10 electrons, right? So nuclear charge will not be distributed that much. So what will happen? The size of this will be more. Or you can say as ionic charge increases, size automatically increases. You can learn that relation directly, or you can apply that form logic behind key when the number of electrons and protons are same, when the protons are more than electrons, when the protons are less than electrons, right? What about these things? What about these two? O2 negative and this one. O2 negative and this one. The atoms are different, right? It is like nitrogen, oxygen, right? This is along the period. Along the period, size is decreasing here, right? This is size is decreasing. This is nitrogen and this is oxygen, right? Here the size is decreasing, so it will be like this. Nitrogen will be more as compared to oxygen, right? When the number of electrons are also same, right? Because it has how many electrons? 7 plus 3, 10. It has 8 plus 2, 10 electrons. These are basically isoelectronic to each other, right? These two are isoelectronic. Isoelectronic. When they are isoelectronic, as atomic number increases, the size decreases. Atomic number of nitrogen is 7, oxygen is 8. Atomic number increases, size will decrease. So nitrogen will have more size as compared to oxygen. That is 3 negative, this is 2 negative. So it will be like this. So this particular answer is correct, right? Then you have oxygen, fluorine, neon, that you can completely see that oxygen and fluorine, that is not correct. Then Na positive, F negative, O2, right? O2 negative it must be, right? O2 negative. It has how many electrons? It has 10. It has 10. It also has 10 electrons. Now, as the size is increasing, same isoelectronic it is. It is also isoelectronic. It is also isoelectronic. Now, as atomic number here is increasing, the size is also increasing. That is wrong. It should be like this. Na positive, right? Firstly, though you have fluorine. Firstly, though you have oxygen, then you have fluorine, then you have sodium, right? As the atomic size is increasing, this should decrease, right? So it will be like this. Oxygen maximum, then fluorine, then this. It will be like this. Okay? Understood? So I have given you the right orders also of all these things. Anything can be asked to you. Okay? Yes, beta? Next question. Ionic radii. What are you talking about ionic radii here? Inversely proportional to effective nuclear charge. That it is as the effective nuclear charge is increasing, right? Effective, that is attraction is increasing. The ionic radii will decrease. That is true, na? That is true. Directly proportional to effective nuclear charge. That means as the effective nuclear charge is increasing, ionic radii will increase. Will that increase? If nuclear charge is increasing, attraction is increasing, size is going to decrease, right? So that will be inversely proportional. Directly proportional to square? No. Inversely proportional to square? No. Definitely no. Right? So answer is going to be A. Answer is going to be beta. A is going to be the correct answer. Okay, Ji? Yes. Beta, the light, they are saying it will come at 2 p.m. So I really hope that this board can work till 2 p.m. Let's hope, let's pray. Let's pray to God, beta. Let's pray to God. Now, the correct order of decreasing ionic radii among the following isoelectronic species, right? What is the correct order of decreasing ionic radii? This is 2010 AIMS question, AIPMT question, right? Now, can you see that these are, firstly, so let us see, are these isoelectronic or not? Correct decreasing order of ionic radii, right? Ionic radii, beta, they are talking about. Everybody in the chat box, everybody in the chat box, sulfur, potassium, calcium, chlorine, okay, sulfur. 4 things is given to you, right? Firstly, so there is potassium, then there is calcium, then there is sulfur, then there is chlorine, right? It's like this, right? It's like this. It's a very good question. It's a very, very good question, right? 17 plus 1, 18, 16 plus 2, 16 plus 2, that is also 18 electrons. Potassium, and this is calcium, right? Again, this will be plus 2, 20 minus 2, that will be 18 electrons. 19 minus 1, 19, 20, again 18 electrons. So this, so I have given you hint that this is isoelectronic. Now you need to see the atomic number, how they are increasing, right? How they are increasing. Okay. So beta, remember, this belongs to 16th group, this belongs to 17th group, right? But this has 19, 20, it has 16, it is 70. So least is this one. If this is the least atomic number, it will have maximum size, right? Then there is chlorine, then there will be potassium, then there will be calcium, right? So C for Capto is the correct answer. Okay. So firstly, you need to identify, usually these ions and all are isoelectric only, right? Then you need to understand that, okay, atomic number, ionic radii is inversely proportional to atomic number. That's it. Okay. Peter, just give me a minute. I need to urgently call firstly. Just give me a minute. Okay, so sorry, bye guys. Now, what is the answer for this one? What is the answer for this one? I was talking about this only so that our life cannot go anywhere. The species of argon K positive and calcium positive. Argon beta, that has 20, right? That is, sorry, 18, right? Then you have potassium positive, 19 minus 1, that is 18. Calcium 2 positive is also 20 minus 2 is equals to 18 electrons, right? It is increasing down the group. So what will happen? The size is opposite. The ionic radius is opposite of that, right? So argon will have maximum. Argon will have maximum. Then there will be potassium. Then there will be calcium. So C is the correct answer for this. How B? Argon, then potassium, then calcium. B, how you are saying? B, how you are saying, beta? Argon, so how can it be in middle? As the atomic number, it is inversely proportional, now. It is atomic number is inversely proportional. This is, size is increasing. So that means this is going to be have less, then there will be this, then there will be this. Right? Because they are inversely, they are isoelectronic species. Okay, so C is the correct answer. Right? Okay? Yes. Then we have the next thing, that is ionization energy. Now, what about this ionization energy? Anybody? Anybody? Tell me one thing. What is this ionization energy? It is you have this atom, right? You want to take out this electron, right? These are your parents, this is you, your friends wants to take out you to some party. So what will happen? Your friend should give energy, right? Okay, your friend is going to give the energy. Sorry, yeah. So what will happen here? So you will have to take out, you will have to you can say the electron. To taking out the electron, there is some energy must be required by that electron, right? Only then it can you can take out that electron from that atom, right? That is called the ionization energy, right? That is basically when you want the electron, when you want to take out the electron from an atom, that is called the ionization energy, right? To take out the outermost electron from the atom, from the shell of from the outermost shell of an atom, that is called the ionization energy. Okay, that is what we call ionization energy. Yes, bacha, this is what we call ionization energy. Ma'am, we check only positive or negative. Means positive or negative you are talking about here? We check both. Number of electrons we have to check, right? Number of electrons we check, these are isoelectronic, then we will apply this formula. Okay, energy required to remove loosely bound valence electron, that is the electron of outermost shell. Now beta, if you want to take out, for example, successive ionization energy means you have, for example, one sodium, you have taken out one electron from here, right? That is Na positive plus electron. Now this energy is called ionization energy of 1. This is called IE1. When you take out electron from Na positive, that is going to be Na2 positive plus electron, right? That is going to be IE2, right? Again you taking out electron from this, right? That is Na3 positive plus electron, that is going to be IE3. Now as you can see that ionization energy required to take out the electron from the first thing, okay, you have observed this thing. This though you have already seen, because after that what will happen? It will have 10 electrons, right? It will have a configuration of 2,8, right? That is a stable noble gas configuration it will have, right? So here it will have 11 electron, it will have 10 electron here. So easily it can take out that electron. So to take out electron, right, from a neutral atom, it is easy, right? There is no positive charge here. There is no attraction, right? The size is not less. As I told you, the size of an anion of a cation is less than as compared to neutral atom. So here neutral atom has a larger size. So larger size means the outermost electron is away from the nucleus. But smaller size means the outermost electron is very close to the nucleus. So what will happen here? To take out the electron from this Na positive, firstly, so it is a cation. Second thing, it will be having 9 electron here. That is not a very stable configuration. So it will be too large, or I would say impossible, right? So that is why even if I talk about any normal ionization energy, generally IE1, then you have IE2, then you have IE3, right? Firstly, you have ionization energy of first, then you have ionization energy of second, then you have ionization energy of third. That means if I talk generally to you, if I talk generally, not even sodium I will talk about, okay? Atoms I will talk about in the next page. Firstly, let us talk about a general thing, that you have M, you have taken out electron, that is M positive. Then you have M positive, you have taken out electron, that is M2 positive. You have M, or you can simply write it like this, okay? You can also write it like this. You have taken out electron, that is M positive plus electron. Taken out electron, M2 positive plus electron. Taken out electron, that is going to be M3 positive plus electron, and so on. If I call it IE1, if I call it IE2, if I call it IE3, that means in the first place I am taking out electron from a neutral atom. That is easy, right? There is no positive charge there. There is no like very high Z effective here. But when I am taking out electron from a cation, that is very difficult. So that means the ionization energy in a successive atom, in a successive ionization energies will be like this. Generally, it will be like this. This is, I'm saying generally, I'm not saying always. I'm not saying always. For example, you have something like this. You have magnesium, right? Or you have, what is the general configuration of magnesium? That is 1s2, 2s2, 2p, 6, 7, 8, 9, 10, 3s2. This is magnesium, right? This is magnesium. You always have to be ready for this thing whenever you are doing the questions. Now, for example, they are saying Mg positive. That means you are going to take out electron from 3s. That will be 1s2, 2s2, 1s2, 2s2, 2p6, 3s1. Taking out electron from here, that will be 1s2, 2s2, 2p6, 3s0. Right? Now, when you take out electron from here, this ionization energy is IE1. This ionization energy is IE2. Now somebody is asking you to take out electron from here also, right? So Mg3 positive, right? 1s2, 2s2, 2p6, right? This is 0 only. You have to take out electron, that means it is 1, then it is 0, right? Now you have to be like this, 2p5. As you can see, this was a stable configuration, stable, fully filled configuration. Now, if they ask me here, this is ionization energy of third. Here, ionization energy will be so much difficult, right? Here, what you will see that, in this case, taking out electron from the third thing is nearly impossible. It is very difficult. And two, if I talk about this particular case, then ionization energy in first and second, right? In the first case, this is not a stable configuration, not stable configuration. It is 2p6, 3p1, not a stable. It is like a noble gas configuration, fully filled stable configuration. So here the ionization energy of I2 will be, second ionization energy will be less as compared to IE1, right? Okay. So as soon as it will take out one electron, it is ready to take out other electron also. That is why you never see this thing. You never see Mg positive. You never see this thing. You will see Mg2 positive. You will always see Mg2 positive. So if I talk about this particular thing, if I talk about that this is the general trend, this is a general trend that usually this happens, but otherwise it depends on the electronic configuration as well. Because here, as soon as you take the first electron from 3s, it will automatically it just need very less energy to take out the second electron also. So there will not be very large difference because it is going to get into a stable configuration. Whenever it sees everything in this world wants to be in a stable configuration, right? So as soon as it is able, I will see a stable configuration here, it will take out the second electron also from 3s and becomes a stable configuration. After that, taking out electron from here is so difficult that it is nearly impossible, right? It is nearly impossible. Same happens to sodium, aluminium. Why you see Al3 positive? Because Al3 positive is this configuration, right? So that means as soon as you will take first electron, second and third will be very easy because there will be very less energy gap that will be required then. Okay? Yes, beta? Okay. Now, beta, you have the next thing, that is, if we talk about the effects here, if we talk about along the period, so when I talk about along the period, right? So always first thing to remember that I talk about period, that means size is decreasing and IE is always inversely proportional to size, right? So if size is decreasing, that means ionization energy will increase here, right? Ionization energy will increase here. Second is, if I talk about a group, size is increasing down the group, right? That means ionization energy will decrease. Size is increasing, ionization energy will decrease down the group, right? So in nutshell, you can say that as the Z effective increases, attraction increases, right? If attraction increases, size decreases. Size will decrease. If size is decreasing, right, it is very difficult to take out the electron. So ionization energy increases. Because size is very small, it is difficult to take out the electron. If I talk about these two things, there is first thing, this thing. This is a bigger size. Take out the electron from here is easy because it is inside the nucleus. There is a nucleus inside it. It is very easy to take out electron from here. Then I talk about this thing, right? In this thing, size is smaller. Now it is more closer to the nucleus. So it is difficult to take out the electron. Here the size is so less that it is easier to take out the electron when we compare these two things, right? Okay? Yes, beta? Also Fe2 positive, Fe3 positive. True that, right? Okay, bacha? That we will do in D block, beta. That we will do in D block, right? Now let us talk about the exceptional trends here, right? Now let us talk about the exceptional trends here. So here, beta, you can see very weird exceptional trends. Firstly, though, you will see this thing that this is a very important question. Very, very important question. It is asked so many times in your previous years, right? So see, I am saying that this is along the period. Along the period, size is decreasing. It should increase. Firstly, though, size is decreasing, right? Size is decreasing. It should increase. Ionization energy should increase. That is my thinking. But what exactly happens here, right? This part and this part, you will see a change. That you were assuming it to be like this. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Neon I am not going to talk about because noble gases, right? They don't want any disturbance. They are like, I am very happy with what I am. I don't want your electron. I don't want to give any electron. So it is very difficult to take out electron from them. They are not nearer to noble gas configuration. They are noble gas configuration. So it's like you can never take out electron from them. It is nearly impossible, right? So ionization energy of noble gases are the maximum in entire periodic table, right? This you can write here. Ionization energy of noble gases is maximum in entire periodic table because it is very difficult. So I'm not going to talk about noble gases and all, right? So here what you will see that, ma'am, this should be the case. Ma'am, this should be the case. Size is decreasing. Ionization energy should increase. But leave one place, box here, then leave one place, then one box here. Leave one place. Now what will happen? Make it an exchange here. Lithium, boron, beryllium. This is carbon. This is oxygen, nitrogen, fluorine. This is the correct order. Now what is the reason behind that? If you tell me the electronic configuration of this one, beryllium, right? Hydrogen, helium, lithium, beryllium, boron. Beryllium is 4, right? So it is 1s2, 2s2, right? It is 1s2, 2s2, 2p1. What about this nitrogen, oxygen? Nitrogen 7, right? 1s2, 2s2, 2p3, 3, 4, 5, 6, 7, right? 1s2, 2s2, 2p4. Now you see, this is a stable configuration, right? It is a fully filled configuration. This is also a very stable configuration. This is half filled configuration. These two are fully filled. This is half filled. In this, both of them are fully filled. So beryllium and nitrogen have stable configuration. Stable configuration. Whenever you will see a stable configuration, ionization energy will increase because it is very difficult to take out electron from a stable configuration. You cannot take out, right? That is why you will see that the ionization energy of beryllium will be more than boron. This will be lithium, then you will have boron, then you will have beryllium, then you will have carbon, then oxygen, then nitrogen, then fluorine, right? Out of this, neon will be maximum, right? It will always be maximum, right? So this is the correct order. It will always be, there is no talk about this noble gases only. Always they will have maximum in that one period, right? Okay, bacha? Yes. Now, bacha, you have the next thing. Now you have the next thing. Acha, firstly, though, we talked about the second period, na? Acha, about the third period also. If we talk about the third period also, let us talk about the third period also. You tell me the right configuration of third period also. This was the second period, na? The third period also. Sodium, magnesium, aluminium, right? Sodium, magnesium, aluminium. Silicon, phosphorus, sulfur, right? I think that is enough. Chlorine, right? Now, the trick is you don't need to write all these electronic configuration. Leave one place, then box here. Leave one place, then box here, right? Then inter-exchange these things. Inter-exchange this, and it will be sodium, then you will have aluminium, then you will have magnesium, then silicon, then sulfur, then beta you will have phosphorus, then chlorine, right? Okay, why are you deleting the messages? Beta, focus here, right? Beta, this is not a dating app, okay? This is not a dating app. Zubair, this is seriously not a dating app. You can go to any dating app. There are lots of dating apps in the market. Go and talk to as many girls as you want. So many of them will be boys only. In the picture of girls, there will be boys, right? You can talk to them. I have nothing related to your life, like, but don't disturb people who are studying here, okay? Beta, are you even there? Are you even there? I mean, I can't see your comments, nothing. Am I teaching the walls here? Am I just, drinking kada and all for the walls here? I am teaching day and night for you guys, but there is no reply from your side. Dating app, you have made this channel. Okay, then I will also take break. When I see your message, only then I will talk. I can't see your messages, or you are not writing anything. I am seriously saying I will not say anything if you don't type anything in the chat box. I'll be quiet only. Okay, I'm standing there silent. I'll be silent here. You want to test my patience? You can. Only one students want to talk, right? Only Savita is there. I want to see how many of you are actually studying. Type whosoever is studying, write it down in the chat box. Yes, very good. 3 students. Others, it's in my class you can't do like, okay? This is my phone. Ma'am is talking here. The phone is aside. I have kept the phone. Then I am watching something else. No, beta. Right? For that, yesterday I slept at 4 p.m. Right? Making all these slides for you. Right? I woke up at 9. I have just slept for 3 hours. Not for this. Not for this. Okay? So, if you can't appreciate the efforts of teachers, then I am seriously saying, then no, that is not going to work, right? Chalo. Okay. Now, as you can see, beta, this was the third period. This is the ionization energy, second period exception. This is very important exception. Then you have this very, very important exception. This is a simple trick. The thing will be same only that this magnesium, right? This magnesium, you will have aluminium here, right? Then beta, this thing is same as that thing, right? It is same as that thing because aluminium is going to have a stable configuration. That means it is going to have 1s2, 2s2, 2p6, 3s2, 3p3, right? Similarly, beta, the sulfur is going to have a stable configuration, right? Okay, the sulfur is going to have a stable configuration. 6, 10, this is 6, 7, 8, 9, 10, 11, 12. Wait, this I have written the equation of this phosphorus, right? Wait, so let me write here. 3, 4, 5, 6, 10, 11, 12, 15. Here so I have written this thing, right? Okay. It is going to increase and not decrease. I think you guys are sleeping or what? Chal, okay, this is going to increase, but these are the exceptions. I am also highlighting the exceptions here. Okay, I am highlighting the exceptions here so that it will be easy for you to learn these, right? That is because of the stable configuration. Now, beta, the next thing we have is P block. In P block, what will happen? We are going to talk about this thing. What will happen? Because of the poor shielding effect of 3D electrons only, the reason is same. Because of the poor shielding effect of 3D, what will happen? The size of, because when you are down the group, you are saying ionization energy, size is increasing, ionization energy should decrease. It should be like this. B, then it should be Al, then it should be gallium, then it should be indium, then it should be thallium, right? It should be like this, right? And here you have F electrons. Here you have F electrons. What happened here? The F electrons, because of the lengthenoid contraction, and this gallium because of the poor shielding effect of 3D electrons. This is the actual order. Now this becomes the actual order. The effect of lengthenoid contraction is so large that it even exceeds the gallium and aluminium, right? So it is so much large, right? Okay, it is very large. Now when we talk about gallium, it is definitely more than as compared to aluminium because of the 3D electrons, right? F has even poor shielding effect as compared to D electrons. That is why this becomes the actual order, and same in case of this. This should be calcium, silicon, then germanium, then tin, then lead, then आपके पास this, right? So what will happen down the group? Ionization energy should decrease, right? It should decrease. It should be like this. What exactly happened here? See what exactly happened here. This you can see. This is not the actual order. This is not the actual order. This is the, wait, it is written here wrong, right? So I will just mark it because this is not the actual order, okay? This is the expected order they have written here. This is not the actual order, right? Same thing will happen here. Same thing will happen here. Same thing will happen in case of this also, because here also there will be 3D electrons. Here also in lead there will be 4F electrons, right? So same thing is going to happen. Pb is going to have more ionization energy. It is not going to have the least ionization energy. Okay? Yes, then that will also be the exception here, right? This will also going to be an exception here, right? Okay, beta, the same thing is written here. Then beta, you have this thing, irregular trends I am mentioning. I have just mentioned you all the irregular trends that are there. In the second period, it is expected is this one, but real is this one. This is expected and this is the real trend, right? Then expected is this one. This is the real trend. Okay, here you will see this one because of the stable configuration. Now expected in the fourth period again, you will see this, and here also you will see this, right? Leave one place, then mark a box here, then leave one place, mark a box here, then leave one place. This is how you are going to inter-exchange this and learn the correct order of that, right? Then beta, you will have this thing. This is the fifth period, this is the sixth period, right? This has a regular trend. Why? Because in the fifth and sixth period, other stuff will also include, right? That will not do here. We will do that in coming classes of P block and DNF block, right? But till here, these things are very important for you. These three are very important for you, and this will not be asked, right? This will, if you ask me, this will not be asked in your paper. This will be asked because exceptions are asked. Exam is not from a regular trend. Exam they ask from a irregular trend, from the exceptional part of inorganic chemistry, right? Okay. Then beta, what about this one? Across the period only, all these things, right? Beryllium, magnesium, calcium have fully filled ns2 orbitals. This have half filled electronic configuration. That is the reason you have these exceptions there. Okay, understood? Then you have next thing, this, as I told you, this is in the group aluminium. This is expected because down the group ionization energy should decrease. But what exactly happened? This becomes almost similar. Why? Because of the poor shielding effect of d block d electrons. And what about this thallium? Why it is more as compared to indium? Because of lanthanoid contraction, right? That is why actual order is this, what we observe, right? Actual order is this, what we observe. Now, what we say, down the group ionization energy should decrease, right? So this is the expected order. This is the expected order. But in reality, what happened? In reality, this got reversed, right? Because of the lanthanoid contraction of lead. Lanthanoid contraction of lead, 4f, poor shielding effect of 4f orbitals, 4f electrons. Here you will see exception in this case. Okay, you will see exception in this case, right? So these are very, very, very important exceptions. You will see direct questions based on this. Now beta, what about this thing? This is your 4D electrons, right? In your 4D, I am saying this is your 3D, like 3D elements. So in this beta, what you will see, there is very irregular trend. Okay, there is very irregular trend of the ionization energy. This is a slight increase due to increase in Z effective, but trend is not regular. That is why the questions are not asked from here. When there are exceptions, but there is definite exceptions, then the questions are asked from there. But then when there is very irregular trend, then the question is not asked from there. So you will see that firstly, sudden jumps from copper to zinc, then you will see from Ag to Cd, then there will be from gold to mercury, right? That is why this is not actually asked in the exams, right? Okay? Yes, bacha? Yes, beta. Now, one more thing here, that if you want to learn the trend of group number 13, if you want to learn the trend of group number 13, right, there are two ways to that. You can also learn it like this. Like this. It will be like this. Okay? It will be like this. So, B, A, L, G, A, IN, TL, right? So you can write down the order here. That is B, then it will be maximum, then it will be Al, then it will be gallium, then it will be, after this there will be thallium, right? Then there will be gallium, then there will be aluminium, then there will be indium. This is the way to learn that trend, because this has so many irregularities, right? Expected was this thing. Expected was this thing. Right? This was expected. This was expected. But this is the wrong order. So this, so I told you the reason behind that. This is because of F electrons, length-rod contraction. This is because of 3D electrons. But how to learn this? Make a W like this. First is this one, then you will see this is the second one, then this is the third one, then this is the fourth one, then this is the fifth. Right? This is how you can learn this. Right, beta? Like a W shape. Okay? Okay, beta? Yes. Then, now this is the 3D electrons, right? This is basically D electrons, right? You can see a change here, ionization energy. Firstly, it is going like this, stable, increasing, then slightly decreasing, then increasing, then again decreasing, then again increasing. And here also decreasing, then increasing a little bit, then increasing, decreasing, then it is going like this. Here also it is decreasing, increasing. There is no regular trend that you can see along all the series. Right? There is very irregular trend here. So let's skip that. But yes, when we will do the D block elements, right, then we will understand what is the highest element, which has highest in a particular series. We will learn that which has the highest ionization energy, which has the lowest ionization energy. That can be asked, but a direct trend will not be asked from these series, right? Okay. Now, yes. Now this is again very, very important, right? Now ionization energy of 5D, then you have 3D, then you have 4D. That means down the group what should have happened, right? It should be like 3D, it is 4D, it is 5D. Down the group ionization energy should decrease, right? But what happened? Because of lengthenoid contraction in 4F, this jumped to this side, right? This jumped to this side. This is the reason behind the irregular trend of group number 13, because in that case it was highly dominating, right? So the answer will be 4F electron. The ionization energy of 3D series is nearly equals to 4D series, or 4D is less than 5D series. Why? Because of the lengthenoid contraction, that is a poor shielding effect. Only exception is this one, that is this scandium and this ytterbium, and then you have lengthenum, right? Okay, this is the only exception. You can see from here also. Okay, that is the first element that is not written in the graph. Okay, it is not there in the graph. It is not written in the graph only, right? So that is the exceptional. Now let us do this question, 2019. I am giving you, you don't need to do other exception apart from this what I am teaching you, right? Because that will not be asked. All the exceptions that will be asked to you, I have collected those exceptions. Only these exceptions will be asked to you. Nothing will be asked out of what I am teaching you today, right? Why? Because already this they have never asked, right? This they have never asked, but I have taken this also, right? Usually they ask these very general trends, right? Okay. Now beta, what about this one? For the second period elements, the correct increasing order, this is frequently asked question, right? Lithium, beryllium, firstly you will see there will be exchange here, inter-exchange here. Nitrogen, oxygen, you will see exchange here, right? Okay, so answer is going to be, everybody, answer is going to be, yes, answer is going to be C, okay? Answer is going to be C. Then what about this one? Which of the following electronic configuration of an atom has the lowest ionization energy? Lowest, that you can see from the, see, this is half filled, this will have maximum. This is fully filled, maximum, too much, right? This wants to gain one electron. It is like, why would I lose one electron? If I gain one electron, I will be a fully filled configuration. This is saying if I lose one electron, then I will be a fully filled configuration. So I want to lose. Okay, so C is the correct answer, right? So C is the correct answer here. Then what about this one? In which of the which electronic configuration of an element has abnormally high difference between second and third ionization energy? Which has abnormally high abnormally high difference between second and third, that there is very large difference between ionization energy. So you need to see this. If it loses one electron, it will be a fully filled, right? After that, there will be abnormally very high difference between energy of one, ionization energy 1 and ionization energy 2, right? What about this one? If it loses one electron and then it loses second electron, third will be very easy. So this will also not be true. If it loses one electron, that will be 3p1, and then it loses two electrons, that is 3p0. Now it is in the fully stable configuration, right? Then beta, it is not going to lose other electron. It is like, it is very difficult because I am fully filled here, right? I am very stable configuration, so I don't want to lose anything, right? That is why C will be the correct answer, right? That is why C will be the correct answer, because there will be very high difference between ionization energy of second and third, right? Okay? Yes? Wait. 2 electrons, then this. 1 electron, 2 electron. Acha, this is to even more, na? This is to even more, because here though it was like this, 1s2, then 2s2, 2p6, it will become 3s2. But here it will become 1s2, 2s2, 2p6. If this was not the option, then answer should be C. But now, as they have given you a noble gas configuration, this is a noble gas configuration, this is even more stable as compared to this. This is only fully filled. This is having same as noble gas configuration. This is even more stable as compared to that. So this is going to be the highest, right? It is going to have highest ionization energy. Right? That will be abnormally very high difference, right? Okay. Then beta, what about this one? What about this one? The correct order of decreasing second ionization energy they are talking about. Okay, titanium, vanadium, chromium and manganese. Okay, okay. Second they are talking about, right? First we need to write the electronic configuration of these, right? This will be titanium will be 22, that is argon, 18, 4s2, 3d2, right? Then you have vanadium, that is argon, you have 4s2, 3d3. Then you have chromium, that is going to be exceptional configuration you have to write, that is going to be this, right? Then you have manganese, that is going to be argon, right? That is 4s2, 3d5, right? So they are saying second ionization energy. That means, second means take out 2 electrons, take out 1 electron firstly, then you will see which is more stable. Take out 1 electron, so it will be 4s1, 3d2, right? Take out 1 electron, 4s1, 3d3. Take out 1 electron, acha, this is going to be a decreasing order. This is going to be have maximum. Chromium should be maximum, so A is the correct answer. Chromium is maximum, so A is the correct answer, right? 4s0, 3d5. It is 4s1, 3d5, right? So after taking out 1 electron, it is in a very stable configuration. So it will not want to take one more, it will not want to give one more electron, because it is a very stable configuration, 3d5, 4s0, right? So it is like, okay, I am half filled, very stable configuration, no other electron. So maximum is this one, right? So A is the correct answer, right, bacha? Okay, done? Done, bacho? Let us jump to the next topic. Yes, now what about this electron affinity? What is this electron affinity? Anybody? What is this electron affinity? Electron affinity means that if I want to give electron, right? But there is a difference between electron gain enthalpy and electron affinity, right? So let us discuss that. Firstly, though, both means that you are going to give the electron, right? You are going to, firstly in ionization energy, you are taking away the electron. Now you are giving the electron, right? That means more is the tendency to gain the electron, right? More is the electron affinity, right? Okay, more is the tendency, more will be the electron affinity. So if I talk about this, may be positive or negative. If I talk about this, this may be positive or negative. One concept, learn this, that for example I am giving the electron, it will be A negative, right? Again giving the electron to electron, that will be A2 negative. Again giving the electron, it will be A3 negative, right? It will be like this. Okay, it will be like this. Now see this. When I talk about electron gain enthalpy, I represent it by delta HEG. Electron gain enthalpy. This is represented, this is the energy. This is affinity. This is energy. And this is a very important concept, right? This is energy. This is affinity. The tendency to gain electron, right? The tendency, for example, I am like, okay, I am very hungry, I want to eat something, right? Like I am very hungry, I want to eat something. That is electron affinity. That is my tendency to eat it. I want to eat it, right? Then here I am saying how much I have eaten. This is, I have eaten 2 chapatis, 1 pizza, 1 burger. What I have eaten, that is electron gain enthalpy. How much energy it has taken. This is the tendency. Okay, this is the tendency, this is the energy. So always when I am giving electron to a neutral atom, the first electron gain enthalpy will always be exothermic, right? It will always be negative, right? The first electron gain enthalpy will be always be negative, always negative. It is going to you can say it is going to release, it is going to be very happy. So if for example you are very hungry, you're like, oh my god, I want to eat something, I want to eat something. You're very hungry. So when you eat the first bite of that, what will happen? You will like very happy about it, right? Then it is like you are going to release the energy, right? That will be negative. That is an exothermic reaction. But all the other electron gain enthalpies are going to be positive. All the other electron gain enthalpies are going to be positive, right? This is going to be positive, right? All the other electron gain enthalpy are going to be positive. The reason behind that is because this is like, okay, I am full now, I don't want to gain more electron, but we are giving it electron, so this is going to be positive, right? So this is positive, and so on, it will be positive, right? So only first electron gain enthalpy will be negative, that is exothermic. The rest of them will be endothermic. They are going to absorb it, not going to release it. They are like, give me the energy, I will not release anything, right? Okay, now beta, next thing is, if I talk about electron affinity, it has an opposite sign. It has an opposite sign. That means if it is saying that I am going to release the energy, I am very happy, right? I am releasing that, I am very happy after eating that. I am like, okay, I am very hungry. My tendency is positive. I want to eat something. That is why when I am happy, I will release the energy. This is how much happy you are. You are releasing the energy because you are very happy after eating something. But this is your tendency because I want to eat something. But here your affinity is low. You don't want to gain more electron, right? And that is why your enthalpy will be positive. It's like, okay, you are like forcefully giving me something to eat. I have to eat it only, right? Then what will happen? Your tendency is not that much. For example, your mom has make 𝐂𝐤, right? Your mom has make 𝐬𝐿 and all that, right? Which you hate. So what will happen? You don't have that much tendency, but your energy, that will be like, I will absorb that, I will not give you the energy. I am not happy after eating that. Yes? Okay? Understood this? How it is like, this is negative, positive, and affinity will have opposite sign to that. So whenever they ask you, this, electron affinity will be positive, negative. Electron gain enthalpy will be positive, negative. Be very careful in that, right? Okay? Now, next is factors affecting it. What are the factors that are going to affect it, right? What are the factors that are going to affect it? Yes, bachcho, what are the factors that are going to affect it? Firstly, along the period I will talk about. Then along the group I will talk about. Along the period, what will happen? The size is going to decrease, right? So size is going to decrease. That means electrons are very near to the nucleus, right? Electrons are very near to the nucleus. If I give it, see, what will happen here? Z effective is going to increase, right? That means the attractive force is increasing, right? So electrons are very near. This is the nucleus. They are very near to it. So you are giving it some electron because nucleus have a very high attractive force here. They are going to attract that electron. They want to gain that electron. So electron affinity will be large here. Attraction will be more, right? Attraction will be more. So electron affinity will be more here. What about this thing? What about group? Here Z effective is less. Here Z effective is less, right? Repulsions are more. That is why electron affinity will decrease here, right? Okay, size is increasing here. That is why electron affinity size is decreasing along the group. That is why electron affinity is increasing, right? It is very difficult for example, here I am not talking about electron gain enthalpy. I am not talking about that. I am talking about electron affinity, the tendency to gain electron. Okay. Yes, beta. Now, let us do here, not so many exceptions they will ask, right? But still, I will write down few exceptions here, right? That they might ask, right? That they might ask. Okay, Ji? Now, let us write this. The exceptions here. The exceptions here. Firstly, let us talk about the exception of second period. Very rare chances that they can ask you this, right? But still we will not take any risk here because there is a very irregular trend, very irregular. Benny no. Okay, so you will see there is very like large irregular trend here. What is this? Okay, lithium, then beryllium, then boron, then carbon, nitrogen, oxygen, fluorine, neon. What is this? Very irregular trend it is. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So that is why this is very rarely asked, right? Very rarely asked. Okay, beta? So, but you have to learn this. Okay. So I'll just mark here. This you can learn with the help of any trick. Okay. So this you can learn with the help of any trick that you want to make. Right. So I will also try to make some trick on that. But this is not possible to learn it as it is. This will only be possible if you know some trick for that. Some mnemonic you should know for this. Otherwise you are going to totally get lost in this. Right. Okay. But yeah, this is important for you. Now I think we have completed almost. Right? We have completed most of the things here. There are more exceptions to that. The first part. The second is third period. Second is third period. Again, a very irregular trend. Very irregular trend. Not a very regular trend. It's like MgAr, right? MgAr, all nana particle. Then you have C-cal. Okay. So, I know the Hindi tricks to that, but English tricks I have to make, right? I know the Hindi tricks to that, but English trick I have to make for you. I will make the English tricks for these two also because otherwise it will be very difficult for you to learn this. Okay, so those who know Hindi, I will tell you the Hindi trick to that, and English I will make, and after that I will tell you, right? Okay? Okay, bachcho. Now, few important that are asked. These two are rarely asked, but this one is asked. but this one is asked so many times. This is very important, right? This is about halogens. Now, in halogens, what happens, right? This is a very, very important thing. In P block, we are going to do that. Firstly, what you have, fluorine, chlorine, bromine, iodine. In chlorine, you will have 3D vacant orbitals, right? You will have vacant orbitals, and because of that only, right, you will have a vacant orbitals, vacant d orbitals. Because of the vacant d orbitals, what will happen? They will have a vacancy to gain the electron here, right? They will have a tendency to gain the electron. That is why it's like chlorine, then you have fluorine, then you have bromine, then you have iodine, right? So this becomes the correct order, right? This becomes the correct order, right? Okay. Similarly, with other stuff also, with others also, like you have OA से उससे tip, right? So you have this oxygen family. Even here, what happens, because of the 3D vacant electrons, because of the vacant electrons that are here, so what will happen? It's sulfur, selenium, then selenium, then polonium, then you will have oxygen here. What is the reason behind that? Can you tell me why oxygen is at last? Why oxygen is at last? Why oxygen is at last? Because this is also asked to you, right? This is also asked in so many times. DM you can write here. Can you tell me what is the reason behind that? Because oxygen has a very compact structure, right? So it doesn't want to take electron from anywhere else, right? So what it does, because of the paramagnetic nature also that we will study in chemical bonding, right? Because of that, it wants to pair up with the other atom of oxygen only, rather than taking one electron and becoming an anion, right? So that is why it has a very less tendency to become an anion like O negative. Okay, so that is why this is the correct order. Here you will see exceptions here, and this is the exception part is here, right? But these two are full of exception. There is no regular trend. But here is this one exception. Okay? Okay, beta? Yes. Now tell me one thing. What about noble gases? Noble gases, have we written for this one? Let us write here only, right? What about noble gases? Noble gases, as I told you while we were doing ionization and enthalpy also, that they don't want to gain electron, they don't want to lose electron. They are very stable. So that is why it will also be very, I would say, less, right? So it will also be very less. And now you tell me the sign here. Electron affinity and electron Eg positive. Electron Eg. What is the sign of electron affinity for noble gases? This they can ask you directly, because if you know the difference between these two things only, then you will be able to answer that. 0, 0, no. There will be slight number, but you tell me, will it be negative or positive, right? No exact value they are not going to ask you. It is not 0, right? But whether it's positive or negative. Electron affinity. It doesn't want to take any electron, gain any electron. That is negative, right? It is negative. It doesn't want to gain any electron. But delta H, that is electron gain enthalpy, right? After you are giving them the food to eat, what you will say? You don't like that food, but they are forcing you to eat that food. What you will say? I hate it. Right? You will be positive in that. You will be like, okay, I'm not going to be happily and releasing the energy. No, I'm very sad and eating it. So it will be positive here, right? Okay, so this is negative, this is positive, right? Okay, bacha? Okay, so this to we have, chalo. This to I'm going to delete only, right? Chalo. Now you see this side, right? Now you see this side. These are the values, right? You can go through them, but they are not important for you. The exceptions are important for you, right? The exceptions are very important for you. Okay, bacha? Right? This you can see. See this, lithium, then almost 0. then 27, then 122, then nearly 0, then 141, then 328, then nearly 0, right? So this is the this order, irregular order that you see. 53, then nearly 0, then you have 43, then you have 134, then 72, then 200, then 349, then nearly 0, right? So these are the irregular trends, right? Okay, so this is important, that is second and third period. After that they are not going to ask you. Okay, yes beta, this is from your NCERT, same thing is mentioned here, same thing is mentioned here. Okay ji. Now wait. Okay, which one of the following arrangements represent the correct order of last negative to most negative electron gain enthalpy? Electron gain enthalpy beta. NEET 2013 Karnataka question. NEET 2013 Karnataka question. This is from that very weird trend they have asked the question, right? From that very weird trend they have asked the question, right? Very irregular and very weird trend, right? So that was COF though was there, right? So if you know that COF was there, from that only you can answer D is the correct answer, right? But still we will see the actual trend there. So it was COF, then aluminium it was there, right? Aluminium, and then there was magnesium. So it should be calcium, right? So it should be like this, let me, oh god, okay. So you can write here that aluminium, then COF, from there you can answer it that D is the correct answer, right? Okay, yes. Now beta, the next question, next is last of today's topic. We have done size, ionization enthalpy, then electron gain enthalpy. Now last part is electronegativity. Now if I talk about electronegativity, this is basically you have E and A, right? And there are two electrons here, right? Because the electronegativity is same, it's like a tug of war, right? I am okay pulling the rope this side and they are pulling the rope that side. If my strength is same to that person, right? So there will be no tug of war, we will be stable only. I am pulling here, they are pulling there, okay, because the strength is same. But what if this happens that this is A and this is B and the strength of A is more than B? So what will happen? A will pull out the electron with more strength, right? So that is basically what we call electronegativity. That is, in a shared pair of electron to pull the electron, right? That is called the electronegativity. Ability of an atom in a chemical bond to attract a shared pair of electron to itself. It is called the electronegativity. It is there in the bonds, covalent bonds, we can see that, right? So beta, there are so many scales to understand the electronegativities. First scale is Mulliken, Pauling and all. There are different scales for that. Again, I am telling you, numericals are not asked from periodic table, right? They may ask, but there are very less chances. But trends, from trends, exceptions, the questions will ask, right? They will ask the question from trends, exceptional trends, right? So this is going to be ionization potential plus electron affinity divided by 2. That means ionization energy plus electron affinity divided by 2. That is going to be the electron negativity of that atom, right? This is according to the Mulliken scale, right? This was according to the Mulliken scale. So they can give you the electronegativity, they can give you the electron affinity and the value of ionization potential or ionization energy and ask you to calculate the delta value, that is the electronegativity value from that. Then beta, you have Pauling scale. Pauling scale has a little bit, you have to need 2-3 things. First is energy of bond dissociation of A and A bond. Like you have A and A bond, how much energy will be required to break this bond? You have B and B, how much energy will be required to this bond? Then you have A and B, how much energy will be required to break this bond, right? Then beta, you will be able to calculate the difference in the electronegativities, right? So that is going to be 0.208 under root EAB minus under root EAA into EBB, right? So basically, if they have given you the bond enthalpies, then you will calculate by Pauling scales. If they have given you the ionization energy and electron affinity, and then you will calculate with the help of Mulliken scale, right? Okay, yes beta, done. This, so you don't have to do this, right? This will not be asked to you, right? Just remember the formula, right? Just remember the formula, that's it. Okay, just remember the formula. Now I will write, Pauling assumed the electronegativity of fluorine as 4, right? Then he calculated. So this is not important for you. What is important for you to know the values here, right? So I will write the values here. I will write the values of what you need to know, right? All the values that you need to know about this. First is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, right? So this will start from 1.5 and you will add, you will add here, this is 1, this is 1.5, add 0.5, 2.5, this is 2, 2.5, this is 3, then it is 3.5, this is 4, right? So he zoomed it to be 4, then 0.5, 0.5, 0.5, you will say that now this will be the electronegativity of these elements, right? So this is the first thing. Now what about the other few elements, right? Then beta, if I talk about chlorine, if I talk about chlorine and nitrogen, it is nearly taken as same, but chlorine definitely has more electronegativity, right? Then you have CIS, that is carbon, iodine and sulfur. Then you have HP, right? HP gas cylinder, right? Then you have HP gas cylinder. Okay, right? So this will be 3, this is 2.5, this is 2, right? This is how you can, if you know the values of these certain electronegativities, that is enough, more than enough, right? Make comma here, right? So nitrogen and chlorine, if you ask me, chlorine always has slightly more electronegativity as compared to nitrogen, okay? But nearly it is taken as same, okay? See, nearly beta it is taken as same. Okay beta, yes. Now 2-3 more things here. Always from here the answer will be in electron volt per atom, right? The answer will be in electron volt per atom. And always remember that electronegativity of a metal, right, divided by electronegativity no, let's skip this, right? Let's skip this only. Yeah. What else? This so you don't need to remember, right? This so you don't need to remember. You can go through that. You can go through this part, but you should learn this. Okay, this is how you should learn. Then you can go through this part. Okay, that how it is written here. Like I have told you to learn these, and then I have told you to learn carbon, iodine, right? Chlorine and nitrogen. You can see 3, right? Then you have sulfur. I told you where is sulfur, sulfur 2.5, right? See, iodine you have this 2.5, SCC, carbon is 2.5, right? Then I told you hydrogen and phosphorus. Where is hydrogen? 2.1, phosphorus 2.1, right? So all these are important to you. You must learn only these values, okay? Don't go through and cram all the values that are mentioned here. Okay, see, now let us learn the trends. So whenever we talk about size increases, like if I talk about along the period, right? Along the period, what happens? Z effective increases, attraction increases. So to attract that electron also increases. So electronegativity increases. Basically, along the period, size decreases, right? So that means it is inversely proportional to the size, right? Then you have along the group. Along the group, what will happen? Z effective is going to decrease, right? That is why electronegativity is going to decrease down the group, right? Okay. So you can write here that firstly the charge on cationic species. for example, the charge on cationic species is increasing, then beta electron negativity will also increase, right? Whether it's cation, whether it's anion only, okay? Whether it's anion, okay? Whether it's anion, okay? So when I talk about this cationic species, for example, I talk about we talk about this in uh, ionic radius also, right? So when I talk about the cationic charge is increasing, you can write cationic charge is increasing, then you will say the electron negativity will increase, because the positive charge is increasing, it will attract the negative thing, right? But when we talk about charge on anionic species is increasing, because negative electron is more electrons are there, so electron will repel each other. So if you talk about A3 negative, it is not going to attract the shared pair of electrons because it already has extra electrons. So that is why for anionic charge, it is inversely proportional. Okay, it is inversely proportional to the electron negativity, right? Okay, bachcho. Everybody. Okay, now if we talk about this thing, very, very important that we also use in organic chemistry, that electron negativity is dependent on the S character. So greater the percentage X character, greater is the attraction, greater is the electronegativity. Here it is 50-50. Here it is, you can say 70, here it is 2:1, right? So it will be somewhat 75, right? It will be around, not 75, this is 50-50, this is around 25, you can say, right? This was about 30, this will be around 33.3, this will be around 25, this will be about 50%, because it is 1/4, it will be 25, it is 1/3, it will be 33.3, it is 1/2, that is 50%. So the percentage S character is maximum in SP. That is why it is going to attract the electron, because S character means more electrons will be spread out in the S character. That is why it is going to attract the electrons. The electronegativity will be more here, right? So always remember SP, then SP2, then you have SP3. This we will use in organic chemistry also. Then bacha, moving to left to right, this so we have done, right? Then beta, about the metallic and non-metallic character, these are the application of electron negativity, right? So many applications of electronegativity that we are going to do here. The oxides, hydroxides, hydrides, all these things are here only, right? If I talk about metallic and non-metallic character, you know, in a periodic table, only in P block, this is the periodic table, right? Only in P block you will see, here over you will see non-metals, and these are the metalloids, these are the metals, these are all the metals, right? So he is saying, what about these? So metallic and non-metallic character will be defined by the electron negativity. That is, metallic character is inversely proportional to the electron negativity, and non-metallic character is directly proportional. As you know from here, you know, fluorine is like a good non-metal, because non-metallic character is increasing here. Non-metallic character is increasing here. As non-metallic character is increasing, this is highly, fluorine the most electronegative element here, right? Fluorine has 4 electronegativity, that is maximum. So fluorine is the most electronegative element. That is why we are saying that non-metallic character is directly proportional to electronegativity. When electronegativity of the element increases, the metallic character decreases, right? As we go there, as electronegativity is increasing along the period, right? Non-metallic character is increasing, but metallic character is decreasing, right? Okay. Then beta, what about next? Next is bond energy. How you will define the bond energy? How you will calculate the bond energy? Bachcho, how we will calculate the bond energy? If I say that this is A and B, the electronegativity is very high, right? One is very powerful, other is very less powerful, right? So it has, you know, attracted the share per electron in very strong manner, right? So they are saying that delta electronegativity. More is the delta electronegativity. That is, more is the difference between the electronegativity. More energy will be required to break that, right? So when the electronegativity difference increases between two bonded atoms, bond makes stronger, right? And the bond energy of that atom, that bond increases. Bond energy is basically to break that bond. Or I would say it also predicts the nature of the bond, right? We can only just predict this. We can also predict the nature of the bond, right? How do we predict the nature of the bond? How do we predict the nature of the bond? If I say the electronegativity of A and B is equal, if I say the electronegativity of A and B is not equal, in this case, it is going to be a covalent bond, right? Covalent bond it is going to be. Electronegativity is almost equal, right? Okay. But if electronegativity is not like very large difference, so what will happen? It will convert to a ionic bond, right? It will become an ionic bond because it's like one atom, they are not sharing, like the other tendency is not to share the electron, right? One is so powerful that it is going to take only the electron. It is going to, the weak person will give off the electron to the other person, right? So that is why what will happen? Ionic bond will form. Now there will be no sharing and caring. Now what will happen? There will be complete transfer of bond and ionic bond will become, right? Okay. So now let us see how to calculate the percentage ionic character by Henry Smith formula, percentage ionic character, right? How to calculate the percentage ionic character? 16 electronegativity, 3.5 electronegativity square, right? Okay, this is the difference in the electronegativity. So this is how you will calculate. And what about percentage covalent? What about percentage covalent character? That will be 100 minus percentage ionic character. Percentage ionic character. Okay, they will give you either the electronegativity of A and B, then you will calculate the delta of it, put the values and you will get the value. Okay. Yes, beta, for example, I give you this question, that electron negativity difference, or I'll simply write delta X equals to 2. Calculate percentage covalent character. Calculate percentage covalent character. Calculate percentage covalent character. What you will do? Just apply this formula, percentage ionic character, that will be 16 delta plus 3.5 delta square, right? So 16 delta is given to you 2 plus 3.5 delta square is 2 square, and you will get the answer, right? And you will get the answer. What is the percentage ionic character? Calculate it. 16, 2 plus 3.5 into 4, 2 into 4 should be around 5, 60, 2. So it will become around 46%, right? It will come out to be 46%. Now what is percentage covalent character? That will be 100 minus 46, that is going to be 54%, right? Okay, that is going to be 54%. Everybody clear on this side? Clear on this side? Any problem here? This question can be asked. Because students will get confused in Fajan's rule. That is why. Okay. Now beta, let us discuss the other applications like bond length. Bond length beta, that is inversely proportional to the electronegativity because bond dissociation energy is directly proportional, right? So that is why bond length is inversely proportional, right? Because bond energy is inversely proportional to bond length. More is the bond length, less energy will be required. That means there, less is the bond length, more energy will be required to break the bond, right? Okay. For example, I have two bonds here. This is my first bond. Wait. I have this structure. So here bond length is more, here bond length is less. Where bond length is more, less energy will be required to break this bond. Less energy will be required to break this bond, right? Okay, here you have less. So more energy will be required to break this bond, right? So that is why it is inversely proportional, right? Then beta, you have nature of bond, already told you, right? You can take it here. Okay, then bacha, you have this thing again. We have also solved the question based on this. Now let us talk about acidic strength of hydrides, oxides, all of these things, right? All of these things we are going to talk about. Firstly, let us talk about acidic strength of hydrides, right? Firstly, let us talk about acidic strength of hydrides. Chalo. Now, acidic strength of hydride. Should I go with this one? Nature of oxides, nature of this, application, this. Okay. So let's talk about this only. Now we are going to talk about oxides, hydrides, hydroxides, all of these things only. So first thing is hydrides. Now if we talk about acidic strength, what is the acidic strength? It is tendency to give away H positive, right? It means it wants to give away H positive, right? That is, if H positive is easy to donate, then it will be more acidic, right? So let us talk about how H positive can be easy, right? For example, if I talk about HF, in HF, fluorine has a very high electronegativity, right? So electron will already be on fluorine side more. That is why this will easily give off H positive here, right? So it will easily give off H positive because already electrons are present with the fluorine. That is why in a particular period, right, when we talk about period, acidic strength of hydride depends on the electronegativity of MH bond. Higher the electronegativity, greater the acidic strength, right? Higher the electronegativity, greater the acidic strength. So what you will write, along a period mention one thing, you will see the electronegativity of metal, right, is directly proportional to the acidic strength, right? But when we talk about a group, then we will not talk about electronegativity. When we will talk about the group, what we will talk about? A group, down the group, like oxygen, sulfur, down the group, what will happen? So here we will talk about the size. More is the size, more easy it will be to accommodate the negative charge, right? Size of atom. It will be dependent on the size of atom, right? Bacha, tell me how to. I'll give you two examples here. Okay, I will ask you the question. This is the first question. This is the second question, right? I will not tell you anything about it, right? You only answer me. CH4 and then you have NH3, right? Then you have H2O. Then you have HF, right? Second part is HF, 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 HCl, HBr, HI, right? Question number three is, you have to tell me the acidic strength of these. Third is H2O, H2S, H2SC, H2TE, H2PO, right? Now tell me the acidic strength of all of these. First question, firstly identify, this is along the period or group. This is along the period. I will see the electronegativity. Along the period, electronegativity increases, right? Electronegativity increases. Acidic strength will increase. So answer is going to be this thing, right? Answer is going to be this one, right? Okay. What about the second one? Here we will not see the electronegativity. This is group, right? Fluorine, chlorine, bromine, iodine. Down the group, right? Down the group, no electronegativity. Don't say, some students what they will do, that okay, down the group electronegativity decreases. then they will write this as the correct answer. No, down the group don't see the electronegativity. Down the group what you see, the size. Size increases down the group. More is the size. More is the capability of attracting the electron, right? More is the size, heavier the size, right? So it can accommodate more negative charge there, right? So it will be like, or you can say more is the size. You can also learn it with this self. HF is like small size, Cl, then HBr, then you have HI. So here now the bond length will be very large, right? The bond length will be less, again less, very less. Because of that, it is easy to break this bond. It is difficult to break this bond, right? So that is why we say that the electronegativity is not here seen. What we see is the size. This becomes the correct order. Right? This becomes the correct order. What about the next one? What about the next one? Again, it is down the group. Down the group, we will not see the electronegativity. We will see the size. More is the size, more is the acidic strength. So it will be like this. And this question again is asked so many times. You can see your PYQs. This question is asked directly. Very, very important question. Okay, ji? Right, beta? Right, beta? This was about the acidic strength. Then, beta, we will do the nature of hydroxides. Now, beta, let us talk about the nature of hydroxides. Okay? Let us talk about the nature of hydroxides. For hydroxides, we will see OH, basic strength we will see. So, AOH, if electronegativity is more than 1.7, then it is acidic in nature. So, how it will see? Hydroxide is like this. This is a hydroxide, right? There are two cases what can happen. If beta, this bond is broken down, then what will happen? It will be acidic in nature. It will release H positive, right? But if this bond breaks, it will release OH. That means basic in nature. That means basic in nature, right? Okay? Okay, bacha? So, we are going to talk about, let's talk about basic nature here, right? Let us talk about basic nature here. Yes, beta, let us talk about the basic nature here. Wait a minute. I hope I am not missing anything. Oxides, so we will talk about after that. Yes, hydroxides only, na? Yes. Okay. So, whether they ask you acidic nature or basic nature is opposite of acidic, acidic is opposite of basic. So let us write few rules here that basic nature is directly proportional to metallic character. Metallic character you know na, inversely proportional to non-metallic character. Non-metallic character, right? This though you have to know firstly, right? Okay. Now let us talk about along the period and group. Period and this is group. No Z effective we are going to talk about. Period and group. Tell me along the period non-metallic character increases. Metallic character decreases. That means basic strength decreases. Metallic character decreases. Basic strength decreases. Right? That means acidic strength will increase. Right? Acidic strength will increase. I can write one more point here. One more point we can write here, that this is also inversely proportional to acidic strength. Acidic strength. That means acidic strength is directly proportional to non-metallic character. Right? What about along the group? Metallic, down the group, metallic character decreases or increases? It increases down the group. Right? So it is metallic character increases, basic strength increases, acidic strength decreases, right? Okay? Yes, beta? Understood? Should I give you some questions based on this? Right? Should I just remember this thing? Basic directly to metallic, non-metallic this. Metallic, so you know that here non-metallic is increasing, and metallic is decreasing, down the group metallic is increasing. Okay, you have an idea about that. So it will be very easy for you to understand this thing. Now the question here is, if I talk about, let us talk about, firstly, okay. Beta, tell me the answer of first question. Okay, I'm writing the second one. What about this first question? What about this first question? This is along the period, right? This is along the period. Along the period, non-metallic, if they ask me about the basic strength they ask me, right? So along the period, metallic character is decreasing. That means basic strength is decreasing here, right? Basic strength is decreasing. And beta, this is down the group. This was along the period, right? So basic strength decreases, right? This is along the group, down the group. So down the group, what you will see, metallic character increases. That means basic strength will increase, right? So it will be like this, okay? So it will be like this, okay, bachcho? You can write it for the first group also, that is lithium, beryllium, boron, that is lithium, sodium, right? You can write it for that also, right, beta? Okay. Have we talked about the basic strength of hydrides? We have not talked about that, right? Let us talk about the basic strength of hydrides also, right? Basic strength of hydrides. We talked about the acidic strength. Okay, this was the acidic strength, right? This was the acidic strength. This was not the basic strength, right? So what about the basic strength of hydrides? It will be the availability of lone pairs, right? Lone pair is available, they will be more basic, right? Because they don't have OH, right? Hydrides don't have OH, right? So it will be beta, this is period, this is group. If there is no talk about lone pair, then what we will do? Tell me. It's a very important concept here. Now, in both cases, when we talk about the basic strength, this decreases here also, this decreases here also, right? This decreases in both the sides, right? This decreases in both the sides. Can you tell me the reason behind that? Along the period, what we used to see, the concept is same, right? Along the period, electron negativity, right? Electron negativity we are seeing. So electron negativity increases or decreases along the period? Everybody, if we talk about, for example, along the period, I am talking about this thing. I'll give you one example of that, okay? Because see, this is, for example, H2O and I'm talking about NH3. Can you tell me about this? This is along the period, or I would write NH3 and H2O. It has two lone pairs, it has one lone pair, right? Lone pair availability is more here, right? So, but this oxygen is more electronegative, right? This is more electronegative. It is not going to give the electron. Basicity is about giving the electron, right? So as electronegativity is increasing here, electronegativity is increasing. So that is why the atom does not want to give its electrons. It doesn't want to donate the electrons. And when it doesn't want to donate the electrons, that is when the basic strength decreases, right? That is why NH3 is more basic as compared to this, right? That is why NH3 is more basic, right? Though it has one lone pair, it has two lone pair, but the electronegativity of this is more, right? It is not going to give away the electrons just like that, right? Okay, what about this group? What about this group? Group, we used to see the size, right? Okay, so if I talk about, I'll give you one example on this. I'll give you one example. Let us talk about any group. Let us talk about H2O, H2S, H2SC, H2TE, H2PO, right? Now, size is increasing here, right? Size is increasing. So when size is increasing, what will happen? Its tendency to donate I would say, when the size is increasing, it is going to, for example, you have lone pairs here, right? You have lone pairs, all of these have two lone pairs here, right? Okay, two lone pairs will be there. Now, as the size is increasing, right, it will be very difficult. The size is larger. It will be very difficult to give away the electrons. Why? What is the reason? Because the size is large, the atom is large, right? The lone pairs are more diffused here and there, right? The lone pairs are more diffused here and there. They're more scattered here and there. That is because size is large, now that is why lone pair will be more scattered here and there. Right? That is why it will be very difficult for that large atom to give away the electrons. Right? That is why here also the basic strength decreases. The reasons are different. Here it is very difficult to give away the electrons because this is more electronegative. But in this case, the size is more. For example, if I talk about this atom and this atom, right? Here, beta, you have lone pairs. Here you have lone pairs, right? So what will happen here? It doesn't look like that. Okay, I'm just giving you a very approximate. No, this is not exactly how lone pairs work or they look like, right? So don't imagine this thing while imagining the lone pair. This is just to make you understand that how it actually works. So more is the size, this will be more diffused here. Okay, they will be more diffused here, and here they will be less diffused. That is why it is difficult to give away the electrons, right? It is difficult to donate the electron. Now here it is easy to donate because the size is less, right? The concentration of electron is more. That is why it is easy to donate the electrons, right? Okay, bachcho. So remember this thing. Here it is because of electronegativity. Here it is because of size. Okay, ji. Done, bacha. Done, beta. Applications here also we have done. This also done. This one also done. Then let us talk about oxides here. Now let us talk about oxides. Beta, this is more than what is there in your NCERT. This is more than that. Okay. So all the things I have already collected in this thing, right? I have written the pointers, right? I have written the pointers from the NCERT as well so that I don't skip anything from the NCERT, right? Okay. So beta, when we talk about the nature of oxides, whether they are acidic, they are basic, all these things we are going to talk about, right? I think only oxides are left here, right? Only oxides are left. Now, let us see the nature of oxides firstly. Nature of oxides, beta, if we talk about this thing, any EO oxide we are going to talk about, right? Any EO oxide we are going to talk about. So, do you remember that how you used to tell in earlier classes that when any oxide we give it excess of water, right? Then what we have? We have one hydroxide, right? We have one hydroxide, right? Now, For example, this is delta, this is delta dash. Now, if delta is more, there can be two things here. If delta is more than delta dash or delta dash is more than delta. If delta is more, right? So what will happen? Acidic or basic nature? If delta is more, what will happen? Everyone, if delta is more, what will happen? See, two things can be seen. See, you can also see this with the help of that. Okay, there are two things that can happen that I told you earlier also in hydroxide, that either it can give H positive or it can give OH negative, right? This will be acidic, right? This will be basic. So this is what you used to do in your earlier classes, metals and non-metals you have studied. That in earlier classes you used to just cram this thing, okay, any oxide, when on giving it excess of water, if it is giving the H positive, it is an acidic oxide. If it is giving OH negative, then it is a basic oxide. Usually we know that oxides of metal are basic in nature, oxides of non-metals are acidic in nature. This is the usual case, right? But here we are going to talk about this very important thing, that the electronegativity of oxygen and H, right? The electronegativity difference is delta X, right? This have calculated to be 1.4, right? This was calculated to be 1.4. Achha, tell me what is the electronegativity of oxygen? That is 3.5, right? Electronegativity of hydrogen is 2.1, right? So that is going to be 1.4, right? So this means this delta is 1.4, right? So can we write it here, this thing, that just write this thing here, that if delta, right, just write this thing. Now I have calculated the value of delta here, okay? Either though I can write directly, right, that I was writing before, that delta dash is more than delta, delta is more than delta dash, right? For simpler, I can also write delta dash is more than 1.4 or delta dash is less than 1.4, because difference is going to be in this metal, right, that we, metal or non-metal or any element that we are going to talk about, non-metal, metal or non-metal. If it is more than this, right, if delta is more, delta dash, the electronegativity of this is more, right? So what will happen, and if the electronegativity of difference of this is less, this difference is less as compared to this thing, then what will happen? Tell me, in which case it will give H positive? According to you, if I say this is 1.8, it is more electronegativity difference. It has less electronegativity difference. So then it means it is easy to break this bond. OH wala bond, it is easy to break. That means it will give us acidic. It will give us H positive. It will be an acidic oxide. But if delta dash is less, for example 1.2, 1.9, any 0.5, anything, right? So that means this is more. So it is difficult to break this bond. It is easy to break this bond. So it will give us OH negative. That means it is going to be a basic oxide, right? So if they ask you in exam, right, that okay, you have, because this is going to be constant only, O and H only, right? So if they ask you in exam that okay, the electronegativity of this element is this much, will it give an acidic oxide or a basic oxide, right? That you can tell with the help of this thing, right? Okay, beta? Yes. Now tell me one thing. Usually in earlier classes, what we used to study, acidic, or you can study, there are 4 kind of oxides: acidic, basic, amphoteric and neutral. All these oxide questions are there in your PYQs. Directly questions are asked. You have to also know that what are the basic oxides, what are the examples of acidic, what are the examples of amphoteric, what are the examples of neutral oxides. Okay, so basic oxide, firstly I will talk about the basic oxides, right? Firstly I will talk about the basic oxides. Basic oxides are oxides of metal, right? These are the oxides of metal, right? So can you name these oxides? Metals, so beta, you have so many metals, right? So many metals we have. Can you name any of them? Any? In periodic table it is full of metals, right? Only from here you have non-metals. It's full of metals. Any oxide you can name, right? You can name Na, this is O, This is Na2O, you can say MgO, you can say CaO. All these are the oxides of metal, are the basic oxides, right? So many other examples as well. This so you can easily tell, right? Because you know what are the metals in the elements, right? Second is if I talk about the acidic oxides. These are the oxides of non-metals. Now can you give me any examples of that? Can you write it down in the chat box, the examples of that? The examples of that. If I talk about CO2, SO2, right? SO3, right? P2O5, right? All these are the basic oxides, right? Okay. Yes, beta. Right? Why I have written it like this? Because if you give it water, it will make H2CO3. If you give this water, it will make an acid only, right? So it will be H2SO3, right? SO3 you are talking about, it will give us H2SO4, right? And P2O5 will give us phosphoric acid. So here the examples will be CO2, SO2, SO3, right, P2O5 and all the other non-metal oxides, right? Okay, ji. Now, beta, let us talk about the amphoteric oxide, from where the questions is being asked, okay, from amphoteric and neutral oxides. Amphoteric oxides are, beta, those which can react with both base and acid. With base, they will behave as an acid. With acid, they will behave as a base. Like they have a dual nature. Like we were talking about wave and particle. Na? Similarly, they behave as an acid, also a base. Depends on which is there, right? For example, they can also behave like, okay, I'm an acid, right? They can also behave like, okay, I'm in a base, right? So these are called the amphoteric oxides. Amphoteric oxides you have also studied. Like you can learn it with the help of, wait, very simple concept, you can learn it. First is the aluminium, then zinc, then vanadium, chromium, lead, tin, right? I think that's it, right? Yeah. Okay. Now why? Because there are so many oxides of these. It has Al2O3. This is ZNO, right? This forms with the base, this forms aluminium, aluminate, this forms a zincate, right? So now this is B2O5, this is Cr, this is Pb, it forms two oxides, PbO2, this form SNO and SNO2. This is CrO3, I guess, yeah. Cr2O3, right? This is Cr2O3, right? So all these oxides, why I have not written all these oxides? You need to learn this thing only, right? You learn this thing, oxides so you can make, right? You learn only these things, that aluminium, zinc, this forms amphoteric, then vanadium, chromium, lead, tin, okay? VCrPbSn, okay, right? Now what about the next part? What about the next? That is neutral. Neutral oxides are those oxides which don't react with any of this, right? There are just few neutral oxides. They don't react with any. They are neither acidic nor basic. Neither acidic nor basic. And there are just three that you need to learn. And they are very, very, very important. Right? Very, very, very important. Any idea on this? Any idea on this? Any idea? Any idea, bacha, on this? What can be these oxides? Yes, I am expecting that you should know this thing. That is Zn, I am writing CO, carbon monoxide, NO and N2O. These are three very important neutral oxides. Okay, three very important neutral oxides. Yes, very good. These are the three most important neutral oxides. Right, beta? Chalo. Now let us talk about the trends here. Let us talk about the trends here. Let us talk about the trends, right? it is written. Let us talk about the trends firstly. That is along the period and along the period and along the group and along the group. Now, if we talk about the oxides along the period and along the group, right? Along the period, what is increasing? Acidic and basic character we are talking about, right? So, along the period, the non-metallic character is increasing, right? Then what will happen? Non-metallic is associated with the acidic oxide. So, acidic character, acidic oxide will, or you can say acidic oxide will increase, right? Basic oxide will decrease, right? Basic oxide will decrease. Similarly, down the group, metallic character increases. That means basic oxide will increase, acidic oxide will decrease, right? Acidic oxide will decrease. ठीक है जी? Done बच्चा? Now, one question based on this, if I give you one question based on this, Na2O, then you have K2O, What can be the answer to this? What can be the answer to this? Is it increasing or decreasing order? Is it increasing or decreasing order? Increasing or decreasing order, what it can be, what it can be. So this is basically, this is down the group, okay? This is down the group, group number 1. Down the group, I told you that metallic character is increasing. So basic strength will increase here, right? So basic strength will increase here, right? Basic strength will decrease and basic strength will increase and acidic strength will decrease here, right? Okay? Yes? Any other order they can ask you, right? After that, if they give you like BeO, MgO, CaO. Now you tell me what is the acidic character, acidic strength of these oxides, acidic strength of these oxides. So this is down the group, right? That means metallic character is increasing. Basic strength will increase, acidic strength will decrease, right? Acidic strength will decrease here. So order is going to be this for acidic strength. This is the order of acidic strength. This is the order of basic strength, right? Either they can ask you anything here, right? Okay, bachcho? Yes. Then we have oxides of same element. Oxides of same element. Acha, when they talk about oxides of same element, for example, they are talking about that I want to calculate the acidic strength. So what I'll do, for example, they are asking me, Mn, you have so many oxides, so simple oxides we will take, SO2 and SO3. How you will calculate that? This will be number of, okay, just simply calculate it with the help of number of oxygen atoms, that is 2, central atom is 1. Oxygen atom is 3, central atom is 1. So that is 2, so answer will be this, right? Okay, what I did here, the formula, you will see acidic strength is directly proportional to number of oxygen atoms divided by number of central metal atom, right? Okay, so if I give you 2-3 more questions on this, if I give you 2 questions more on this, this is the first question. The second question is, let us talk about P2O3 and P2O5, right? You have to tell me which is more here, increasing or decreasing. acidic strength order, right? Increasing or decreasing. Third is MnO, Mn2, Mn2O3. Yeah. MnO2. How you will calculate this? We will do this in redox reaction. The reason behind that we will do in redox reaction, okay? Yes, this is number of oxygen is 3 divided by central metal atom is 2. This is 5 divided by 2. This is going to be 1.5. This is going to be 2.5. So here it will be increasing, right? This is more as compared to this, right? It will be increasing, not decreasing. Increasing order. What about this one? Here it will be number of oxygen is 2, central atom is 1. Number of oxygen is 2, central metal atom is 2. Number of oxygen is 1, this is 1. So it is going to be 2 divided by 2, it is 1.5, it is 1. So this is going to be this one, right? MnO2, then this is decreasing, right? This is decreasing, right, bacha? Okay. Any problem here? Any problem here? It's last part, even I am now tired. Just 1, 2, 3 more things are left. Okay. Yes, beta. Now, you can easily answer this thing, right? You can easily answer this thing as well. This to I am deleting only, right? Right. Okay. Now, handwritten notes are much better than that. Okay. Now, let us talk about anhydrides. Okay. Now, let us talk about anhydrides. Acid and anhydrides. Okay. Acid and anhydrides. So I am going to write some acids here. Now, very, very simple things we are going to do, right? Okay, I am going to write some acids here and we are going to make the anhydride of that, right? This will be acid. This will be acid and this is anhydride. Anhydride of that. So, firstly I will write H2SO4, right? Then write H2SO3, H2CO3. What else? Let's write, okay, firstly let us do for these three. Okay, firstly let us do for these three. Just subtract water from here. Subtract water from here. Okay, minus water will be anhydride. You just need to take, anhydride means you need to take out the electron. Okay, you need to take out the electron. When you take water from here, this is H2O. 2 hydrogen minus, it will be SO3. That is going to be your anhydride. That is SO3. That is your anhydride. Okay, that is your anhydride. They can ask you out of the following which is the anhydride of an acid, right? So you have to know this, right? Okay, then I add water and see if that is a real acid or not. Now, H2SO3. Take out H2O from here, 2 hydrogen gone, 1 oxygen gone, so it will be SO2. Take out H2O from here, 2 hydrogen, 1 oxygen, it will be CO2, right? Okay, now what about the other part? What about this thing? If they have something like this, that is HNO3, right? HNO3. If they have given you HNO3, ma'am, it has just one H, then how can I take 2H from here? Then take the 2 moles of this, right? 2 moles of this. Now what you have? 2 hydrogen, 2 nitrogen, 6 oxygen. Take out H2O from here, you will have Take out H2O from here, you will have 2 H2O gone, so it will be N2O5. That is going to be the anhydride. Okay, N2O5 is going to be the anhydride. Right? Similarly, if I ask you HNO2, what about this one? Now again there is one hydrogen, so take out 2 moles of this. Now what you have? 2 hydrogen, 2 nitrogen, 4 oxygen. Take out water from here, 2H and 1 oxygen, then it will be N2 oxygen. How many left? 3. N2O3. That is the anhydride. Okay, that is the anhydride. Okay, bacha, any problem till here? Any problem till here? Any problem here? Let us do for the next. Let us do some more acids and anhydrides. Okay. Now, for example, they have given you H3BO3. You know, this is an acid only. It can also be written as BOH thrice, right? Boric acid. They can also give you this thing, right? So, how you will write it? 2 hydrogen, take out 2 hydrogen. What you will get? 2 minus water, you will get H2BO. This you will get. H2BO you will get. H2BO2 you will get, right? H2B oxygen 1, right? Will be H2BO2, right? Or HBO2. H2 will go, na? So that is HBO2, right? So still we are left with 1 hydrogen. And hydride means just take out as many waters as you can take from here, right? So you take out as many water as you can take. This is 1, this is 2, H2O. So now what you will do? You will multiply it by 2. Now what you will have? 2 hydrogen, 2 boron, 4 oxygen. Understood this thing? Firstly, I took 1 water from here, that is HBO2. I also want to take another water. Why? Because I don't want any hydrogen to left behind, right? So what I'll do? 2 moles of this, because in a beaker there is just not 1 or 2, there are million and trillions of molecules, right? So I'll take from 2 moles, but from 2 molecules, what will happen? I'll take about, this is about 2 molecules, I'll take 2 water, 2 hydrogen and 1 water, so it will be 2 boron and 3 oxygen. That means answer is going to be B2O3. That is the anhydride. Okay, that is the anhydride of H3BO3, right? That is the anhydride of H3BO3. Okay. Now, if they give you some 2 different acids like HClO4 and HClO. Now, what you will do? Completely just see how many in total, how many hydrogen you have. 2 hydrogen. Chlorine you have 5, chlorine you have, oxygen you have 5, chlorine you have 2, right? Take out 2 hydrogen and 1 oxygen. You will have 4 oxygen and 2 chlorine. So it will be Cl2O4, right? So answer will be Cl2O4, right? So just subtract water, that's it. Okay, ji, any problem here? Any problem, beta? Any problem? Should I give you one more question? For example, you have HNO3 and you have HNO2 and you have HNO2. What will be the answer then? What will be the answer then? What will be the answer? The answer is going to be 2 hydrogen, 2 nitrogen, 5 oxygen. So 2 hydrogen cut, this 1 oxygen gone, so it will be N2O4. Answer will be N2O4, right? Okay, one more. Now if you have H2SO4 and H2SO3. What about H2SO4 and H2SO3? H2 SO4 and H2SO3. What will be the anhydride of that? 4H, right? Then you have 2 sulfur, 4, 5, 6, 7 oxygen, right? 1 water, if you take 1 water, it will be 2H, 2 sulfur, 5 oxygen. Take 2 water. You have again 1 water. This will be 0 hydrogen. Hydrogen will not be there. Okay. Then you will have no hydrogen, 2 sulfur and 3 oxygen. So it will be S2O3. Okay. S2O3. That is going to be the anhydride. Right? S2O. S2O5. I have subtracted 2 oxygen from here. It will be 6. It will be 5. Yes. S2O5. Right? S2O5. Right? So answer is going to be S2O5. This is very simple. You can do it like this. Okay? Any problem here? Any problem, beta? If you have any problem, write it down. 2 more topics to go. Are you finding it interesting or not? You are hating this. Okay. Next one, beta. Let us talk about oxyacids. Right? Acidic strength of oxyacid. Acidic strength of oxyacids. Right? Oxyacids. Acidic strength. Let us talk about that. Yes, let us talk about that. Now, oxyacids, beta, that is the same. One thing will remain same only. Period. Non-metallic character increases. Right? That means non-metallic character increases here. Acidic strength will increase. Right? Acidic strength will increase. That will remain same. Okay, let me write non-metallic character increases, acidic strength will increase. Right? What about group? What about group? Metallic character increases. Right? In a group, metallic character increases, non-metallic character decreases, acidic strength decreases, basic strength increases. Right? Okay? Okay, bacha? Yes, beta, that will come in maybe 2 to 3 days. Okay, that will come in 2 to 3 days. Okay, bacha. Now, let us talk about this thing. If you're talking about, let me give you one question based on this. Okay, let us talk about one question. First question is H2SO4. I know you already know the answer. H2SO. No, it is H2SCO4. Okay. Second is H3CO3, H3PO4, H3PO3, H2SO4. What about this thing? This is down the group, right? Oxygen, sulfur, selenium. Down the group, metallic character increases, acidic strength decreases. So it will be like this. This is carbon, then you have phosphorus, then you have sulfur. It is. Now see, you have carbon, you have phosphorus. What you can see here, that this phosphorus and sulfur, right, they are in the period, right, they are in the period, phosphorus, then you have sulfur, right. So here what will happen, in the period acidic strength is going to increase, right. For example, I also put, if this one also I put here HClO4, right. So what is going to happen now? What is going to happen now? This is along the period, this is phosphorus, sulfur, chlorine, right. So that is along the period 15, 16, 17, right. Along the period non-metallic character increases, acidic strength will increase. What about this carbon and phosphorus? Like carbon, and this is 4, this is 15, right? It is somewhat like carbon is like group is changed, and the period is also changed, right? So that is why it is going to be like this, right? Why so? Because beta, as you can see, H3CO3, right? This should be H2CO3. Okay, right here H2CO3, right? So this was based on the period, and this is based on both the period and group, the collective effect of that, right? This is the collective effect of that, right? Okay, because we cannot say if there was nitrogen and then you have phosphorus, then sulfur, then chlorine, then you can directly say, but this is the collective effect of period and group, right? Okay. Yes, full periodic table. Oof. Now beta, this also we have done. What we are left with? For one central atom, these are all the oxoacids, okay? These are all the oxyacids. So, for one central atom, if you have one central atom, so what will happen? So, same, or I would say same central atom, not one, I would say same central atom. In oxides, what we did? In oxides for the same element, what we did? Acidic strength is directly proportional to number of oxygen atom divided by central metal atom, right? And here what we will do? Same thing, that is acidic strength is directly proportional to number of oxygen atoms. But there is one exception to this, okay? There is one exception that we will learn about. First is, if I talk about HClO, HClO2, HClO3, HClO4, right? This is atom, central metal atom is same. Second beta, if I talk about, now you need to tell me increasing and decreasing order of these, right? HNO2, HNO3, right? Then you have H2SO4 wala, right? Okay, H2SO4, H2SO3. Now you tell me. These are the oxyacids. Number of oxygen atom is increasing, right? So answer will be this. Number of oxygen atom increasing, answer is this. This more oxygen atom, answer is this, right? More the number of oxygen atom, more is the acidic strength. But there is one, see, we will in P block, in detail we are going to do this. We are going to draw the diagrams and then we will study that why it is like that. Okay, then we will study why it is like that, because now let us understand the exception. Exception is of phosphorus, right? For phosphorus, this is exceptional, and that is why this is asked, right? That is why it is asked, right? H3PO3, H3PO4, right? H3PO4, see, let us start 3, and this is H3PO2. Now, your assumption is that it has more oxygen atom, it should be like this. This is our assumption, right? But actually, it is like this. And this is a very, very important exception, right? It's a very, very important exception. But the reason behind that we will not do today, right? Because you need to know chemical bonding first. After that, we will do that. Okay, in chemical bonding, we will understand that why this is the exception. Right? Note down, this is the exception. Note down, this is the exception. After reading the theories of chemical bonding, we will try to understand why it is like that. Okay, beta? Yes? Yes, bache? Yes, beta, then you need to buy Anavasti of JE, right? Then you need to buy the Anavasti of JE, not this. Yes, beta, everybody, we have completed everything here, okay? So, if in nutshell, if I tell you that what we did here, in nutshell, if I tell you, okay, now everybody be active in the chat box. We are going to conclude all the general trends. Okay, conclusion, the general trends. Firstly, if I talk about this means period, this means group. Okay, so simply I'm going to write, going to draw the arrow here, right? Let's erase this only, right? I'll draw the arrow here. Right? Let us do this. Okay. If I talk about this size, if I talk about along the period, Z effective increases, screening effect decreases, Z effective increases, size decreases, right? Then you have ionization energy increases, electron affinity increases. What else, beta? What else? Electron affinity, electronegativity increases, metallic character, using non-metallic character increases, metallic character decreases, right? Okay, and acidic strength, you know, that is directly proportional to the non-metallic character, right? That is, in the nutshell, we have done this thing. If you know these things, exceptions, then you are sorted, right? At least to learn the exceptions, you should know the general trend also, right? Then beta, here Z effective decreases, size increases, because here so you can write shells increases, right? I want to write it with some other pen. Z effective increases, decreases, repulsion increases, shells also increases, ionization energy, or you can say size firstly, size increases, ionization energy, electron affinity and electron negativity, it decreases, right? Metallic, non-metallic character decreases, metallic character increases, right? Okay, this was the conclusion of today's class. Or you can write one more thing here to learn this. Size is inversely proportional to ionization energy, electron affinity, electron negativity. And if size is increasing, metallic character decreasing, metallic character was decreasing. So metallic character and non-metallic character, non-metallic, right? I think that's it. Anything else we have done? Yeah. Okay. So this is also a very important conclusion, that you must know the general trends. Okay. Okay, bacha, everybody. Yes, happy about it. Now, beta, you have NEET Pedia, right? Just knowing this will not work. You have to know all the other things also. That is, you will get first a very, very important thing. That is, you will get free mock test, right? You will get the free mock test. The link is in the description. This is basically a full package of NEET Pedia. And what are the different things that you are going to get here is, firstly, you will get the free mock test. Then beta, you will get physics, chemistry and biology, right? Complete syllabus, right? Everything in detail will be there. Then beta, you will get for revision. For example, some chapter you are like, okay, I'm very good in this chapter. I don't want to go through that chapter again. I want to revise that chapter. Then you will get mind maps and revision books for that. You will get most important NEET PYQs, right? You will get a NEET question paper of last 5 years with answer keys. You will get NEET 2024 video analysis answer keys. Then beta, you will get detailed list of medical colleges so that you can track that what are the medical colleges that you need to focus on according to your state, right? Then beta, you have all India rank and college predictor, right? So all these things in one package. What you need to do, just download it. The link is in the description. Till now it is for free. For how long it will be for free, we cannot say that. Might be the offer will end tomorrow only, right? So go there, download it and you will be sorted. Yes, beta, everybody. Okay. Now, I want all of you to write it down in the comment section how you like today's lecture. Each one of you that stayed for like so many, it's such a large time that say for around 4 hours here, you are sitting here, right, without even a single break, right? So I want all of you to write it down in the comment section what you actually think about this lecture, where we did everything that can be asked from periodic table. Trust me on that. Nothing can be asked like apart from what I have taught you. That is, I can guarantee you that. Right? You do everything that I have taught you here. Nothing else you need to do. Yes. If you want to revise, what you can do, you can just read the periodic classification NCRT. Right? You will see, okay, ma'am had taught everything. Right? And you will, that will be a very good revision, and do the NCRT questions, PYQs, NCRT back exercise question, in-text question, everything. If for inorganic chemistry, each and every single line of NCRT is most important for you. I have concluded it, but you have to read it yourself also. Okay, bacha, bye-bye, take care. See you all in the next class. Bye-bye. Don't forget to like the session, and I'm waiting for your comments.